me just. Okay. All right. All right. So we're going to do our homework. Let me show you the homework. Okay. All that. All right. So let's look at homework. Homework 1. Write out what will be identified with this run. We're going to write out what will this identify? What will this diff and diff identify? If you lose if you have a treated control group, right? So let me show you. So I'm going to put this over here, and then I'm going to do this airplay. Okay, let me. Okay. All right, so we're going to write that down. This is homework number 1. Okay. What does DID identify if you use an already treated comparison group? I don't have the answer already worked out in front of me, so I'm gonna do it. I'm gonna do it from kind of memory. So here we have our regression. Call it okay. So there's our regression, and we want to know, what does it equal? And we know that it is 4 averages and 3 subtractions. We spent a lot of time showing that, and we have it also in that equivalence dot do and equivalence dot R code so that you can see it in a simulation, but we showed that that was the same thing. And the 4 averages were this. Expectation YK post minus expectation YK pre, big parentheses, expectation YU post minus expectation YU pre. Okay. All right. So step 1, use the switching equation. Use the switching equation and replace Y with either Y1 or Y0, depending on if it's treated. So we'll have here, this will equal expectation Y1K post, because in the post period, treatment group is treated, minus expectation Y0K pre, because in this exercise, we are still going to be assuming no anticipation, and this gives us no anticipation, all right? Minus, here, Ronnie, expectation Y1 U post minus expectation y1 u pre. I ran out of space. Okay. So here, this is the violation. It's not a violation. It's actually not a violation. It's just it's not going to be diff and diff. Because diff and diff assumes that the control group, the comparison group is, well, does diff and diff assume that? We'll get into that. I think probably there's an argument that could be made that the canonical diff and diff assumes no anticipation, Sudva, parallel trends, and a comparison group that is not treated. But here we go. All right, so this right here, what we're going to do is we're going to add in some zeros. So first thing I'm going to add in is this. This is step 2. Add 0. Add zeros. All right. So we're going to say expectation YK 0 post minus expectation Y0K post. All right. That's the first one we're going to add. And I'm just going to do this in a few steps so that you can sort of see it. So we'll go here. I got to be a little careful here. Running out of space. Expectation Y1K. Actually, expectation Y1K post. That's this one. Minus expectation Y0K post. And that's this one, right? And so this is the ATT, right? Okay, so we got, it's like we got, now we've got to bring this down. So now what we're gonna do is we're gonna bring that down. And so we end up with okay. So this is not a parallel trends expression, because parallel trends is only expressed in terms of Y0, not Y1. Okay. So what we're going to do is we're going to add in some more zeros. We're going to use the color blue. I don't have a blue. All right, blue. And I'm going to add in, let's see. Call it step 3. Add in 2 more zeros. All right, I'm going to add in 2 more zeros. Okay, so I go plus expectation Y0U post minus expectation Y0U post. That's 1 0. Plus expectation Y0U pre minus expectation Y0U pre. All right. And so what I'm going to do is I'm going to have to rewrite this whole thing. Whoops. Rewrite this whole thing. It's actually kind of fun, actually, the more that you work with it. It's actually a lot of fun to do this. It's really kind of calming because you're like, oh, this is all logical, right? Expectation, Y0, K, post minus expectation, Y0, K, pre. There's our first trend in Y0. It's our first trend in Y0. Minus, all right? Minus, what we're going to do here is we're going to add in minus here, expectation, oh, okay, so what we're going to do is we're going to add in this one. Okay, we're going to add in that one. So we're going to go expectation Y0U post. And then we're going to put in this one. Minus expectation Y0U pre. So look, that's a parallel trends assumption. This is a parallel trends assumption because notice it's all trends in Y0. It's all trends in Y0. Now, what's interesting is that notice that interestingly, both Y0U in post and Y0U in pre are counterfactual because it's an already treated group. It's an already treated group. Well, you're going to see, Guange, you're going to see it can be, it's the issue is if we leave it in terms of the Y1 and we don't put it in terms of the parallel trends assumption, you're not going to see enough about what the identifying assumption is. Okay. So when you go through these exercises, you're always wanting to get your diff and diff coefficient to equal the average treated on the treated plus a standard parallel trends, and then see if anything else, if there's additional biases that show up. That's what we're trying to do here. So both Y0 in post and Y0 in the pre are counterfactual, right? Because neither of these, if it's an already treated group, then, if U is already treated, we do not observe Y0U ever, right? You don't observe it ever. So therefore that but that's a parallel trends assumption. A parallel trends assumption is change in Y0 equal change in Y0 for two groups. That's what it means. That's what parallel trends assumption means. Change in Y0 for one group equals change in Y0 for the comparison group. And now we've recovered it. But we now have 4 other terms that we've got to deal with. So we've got this, 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 and this. All right. So let's figure out how we're going to do this. It's a minus. So that's what it was. It's a minus. Oops. Let me just double check here. So use expectation. Used expectation Y0U post. That negative was kept there. So it's negative was kept there. And then I just took this one. Oh, I think I had to like fully distribute those negatives to really see this. I think that should have been like negative expectation Y1U post And then I probably use this one, negative expectation YU post. I think I probably was supposed to use this one, right? Because that and this can be replaced. So that leaves me with this positive here. But I think it's fine. All right, so minus expectation Y, hold on. Minus expectation Y1U post, that's observed, minus, oh no, I guess that's fine. I guess that's fine. Yeah, that's fine. All right, so then this is why I struggle a little bit with potential outcomes is it's a lot to kind of carry, even though it's just basic addition. I like have trouble getting the parentheses to look right. And then I like for some reason I can get lost really easily. I was always like this in tests too. I would sort of on the math tests, I would be like, couldn't see the forest for the trees. So I would like mess up a lot by just kind of losing track of terms. All right, so I got that one, and then I'm gonna have here. Okay, so that's this. This is the minus here. This is gonna go minus expectation Y1 U pre, right? That's that right there, minus expectation YU pre, and then I've got a YU pre right there, minus expectation Y0 U pre. All right. Okay, so let's kind of like summarize this, right? Let's like summarize this. See, these right here, guys, look at these. The reason why we do this kind of rearranging is that it becomes a lot it becomes a lot more interesting, I think, when we, what exactly is being assumed. Look, this is an ATT. That's an ATT for you in pre. And this is an ATT. It's an ATT for you in post. Okay. So I'm going to rewrite this here. If we use an already treated group as a control, diff and diff will identify ATT plus parallel trends bias minus change in ATT from pre to post for the comparison group. All right, so I'm just going to call this, I'm going to call this change in ATT. Because see, in the pre-period, the ATT, this is the ATT in the pre-period for your comparison group. Your comparison group is treated. Through this manipulation, we've got an ATT term for the comparison group in the pre-period. So it's been treated already. And we're going to say, well, what is its treatment effect in the pre-period? What is its treatment effect in the post-period? And does it change? Okay. Does it change? Is it the same number? Is the treatment effect changing period to period? ATT plus parallel trends bias minus delta ATTU. Minus delta ATTU. And so what we see here is that if you use an already treated comparison, then diff and diff will identify ATT under these assumptions. Number one, parallel trends in Y0. All right. Number two, no anticipation at the baseline. And here's where no anticipation came in, right? Oops. Right there. So it's coming in Y0K pre. There it is right there. There's no anticipation. So no anticipation is forming part of that parallel trends assumption. Okay. Three, Sutva. But in a way, it's kind of like what I'm not entirely positive is that, you know, your comparison group is treated. So I'm not really sure. I'm not really positive if we're even like satisfying Sutva. So I'm not exactly sure if like Sutva is being violated or if, you know, because you could have an already treated group as a comparison and yet there not be any interference. It's like this is more of a bad control idea. And then number four, group use treatment effects are differencing to zero. Delta ATTU equals zero. You have to assume no dynamics in the comparison group's treatment effect. So that could be two, you could get that in two different ways. The treatment effect is zero. You know, you could get this in two different ways. So like, you know, this could be allowed. This could be allowed if the treatment effect has worn off for the comparison group. Maybe the comparison group was treated like 20 years earlier. Okay. And so right now, like, you know, it was treated 20 years earlier. And so, you know, even though there's like a treatment effect, there's no treatment effect in the 20th year. That's what this like pre-period would be. Because you're saying you're using it in already treated group, but maybe it was like treated 20 years before. So that in that particular period, it's like, it's just like barely doing anything. It's like diminishing returns to the treatment effect. Okay. So if that was true, you know, you could use an already treated group as a comparison group if the treatment effect had worn off. And why that would mean this, that would mean ATT for you grew UP in the pre equals zero. ATT for you in the post equals zero. So that'd be one case. Or treatment effects for group U have stabilized and no dynamics exist. If that was the case, it would be like ATTU pre would just equal ATTU in the post, and there'd be no dynamics. All right. But if your comparison group has at pre and post dynamic changing treatment effects. Because remember, your comparison group has been treated. So therefore, it could have treatment effects. And if those treatment effects are evolving over time, then your diff and diff is biased even with parallel trends. That's what all this showed, is that parallel trends gets rid of that bias, but does not get rid of that bias if you're using a quote bad and already treated control. So if your comparison group has at pre and post dynamic changing treatment effects, then this diff and diff here is biased towards zero and could, depending on the magnitudes, even be the wrong sign. Even be the wrong sign. Because see, remember, it's this. Delta hat equals ATT for group K in the post plus parallel trends bias in Y0 for K and U minus delta ATTU. Okay? Minus the delta ATTU. So see how this is attenuating? It's, so what, so like assume ATTK in the post is equal to 20. And then assume parallel trends. And then assume delta ATT for the U equals 25. Right? 25. So you would get something like that if you had this. Like this would be like, this would be like 55. And this might be like 25, 35, 30. So it went up. So the delta ATT is 25 because it was 30 in the first period or in the pre-period, and it was 50 in the post. 55 in the post. So that's a change in 25. Right? So you'd rewrite it and you'd get 20 plus 0 minus 25. You'd find a -5. You'd find a -5 on the diff and diff, even though the truth is a 20. Even though the truth is a 20. So you see here, and so this is the problem. This is the problem. Our event study graph shows changes in Y0 for K and U in the pre, right? And parallel trends is expectation Y0 K post expectation Y0 K post minus expectation Y0 K pre minus expectation Y0 U post equal minus expectation Y0 U pre, right? So that's what parallel trends is. It is about Y0s. Okay. And the pre-treatment coefficients in diff and diff in an event study are also about Y0. Now, so versus pre-trends are, expectation Y0K, and let's say it's like T minus 2 minus expectation Y0K pre minus expectation Y0 U T minus 2 minus expectation Y0 U pre. So you can see here, like, that is not counterfactual, but this is counterfactual. So parallel trends depends on this one, not that one. Okay. But we use the event study as kind of a heuristic, a kind of an indirect piece of evidence for whether or not parallel trends in the post is believable, because if parallel trends holds in the pre, it's sort of it's not logically required. Just because the parallel trends holds in the pre doesn't mean that parallel trends will hold in the post, right? These are two different variables. Y0K T minus 2 and Y0K post are not the same. So just because they're equal in one period doesn't mean they're going to be equal, equal over 2 periods doesn't mean they're going to always be equal. over 2 periods. But that's sort of the reasoning, right? That's the reasoning. So the event study is our evidence, or one of our evidence for parallel trends, because the pre-trends and parallel trends both use Y0. Can only use Y0. But changing ATTs for group U has no, like, it has no test. Has no test. Because you would be placing if you were to use an already treated group as a control, you're going to really need to have a lot of confidence that the treatment effects are either constant, which you don't know. You don't know because you've not estimated that. You've not estimated the ATT for group U in the pre-period and the ATT for group U in the post. So you don't know that, but you'd have to assume it, which is a very strong, that's kind of a big assumption. And then secondly, or you have to be assuming that it's worn off and you don't know. So the problem is, you don't have any information about the ATT treatment effects for group U at all. So you're just kind of making like a blind assumption, and there's no way to verify it. An event study is not going to help you on this because event studies are only about changing Y0s. They're not about changing ATTs. All right. So this is kind of this is kind of the danger, it's like using already treated groups as comparisons should be avoided because you lack the information needed to justify the assumption of delta ATTU equaling 0. You don't know. You don't know. Homework number 1. I think the last term should be ATTU pre. Charles, where did I get that wrong? Where am I messing up?
I am not sure. I'm sorry.
Sorry, the
different
ATT for U and pre, you've got minus ATT for U and pre.
Mm-hmm.
I think that should be a plus ATTU for in pre.
I think so. But eventually, you still right at the end when you minus the delta or ATT. So it's still right eventually.
Eventually I got it right, but I have an error in here somewhere.
It's just because like the way you've written it now is like,
yeah.
If the treatment effect is the same for the U group in both the pre and the post period, then that actually doubles the bias rather than.
Okay. Yeah. I knew that I think what I've got to do is I got to get rid of the parentheses and then I can see everything and I can like move stuff around. That's that's right. But the final thing is right. So this is the final expression, which is that diff and diff will be attenuated towards 0. Attenuated towards 0, but could flip sign. Yes. Okay. Thank you. So I'll have to play. I'll write up a PDF that I'll share to show it. Does that make sense though? I don't know. Do you guys have what's your reaction to this? Does this make sense? It's a lot of notation, surprisingly, but you can kind of see here how this potential outcomes notation really starts to open up a lot of the assumptions that are kind of behind these standard assumptions that are kind of behind the diff and diff estimator. Yeah, this is precisely go ahead. This is kind of precisely the deformity of two-way fixed effects with differential timing. It uses two-way fixed effects with differential timing, the stuff we're going to do on Saturday. It uses an already treated group as a control. That's what we learned from people like Kirill Borsak, Xavier Yarvel, Clement de Chase Martin, Xavier Clement de Chase Martin, DeHopeful, Andrew Goodman Bacon. It's like they all basically, so like all of this new two-way fixed effects, this new two-way fixed effects literature focused on differential timing showed that the algebra of OLS calculated a coefficient that was partly based on using already treated groups as controls. This exercise that we just did, even though it was in the simple 2x2, is actually the exact same expression that you're going to see Andrew Goodman Bacon discuss on Saturday with his paper, which is two-way fixed effects uses already treated groups as control groups. It can't help it. It can't help it. And so ironically, all of the new diff and diffs, all of the new robust diff and diff estimators, one of the things that really characterizes them is they in estimating the ATT, go out of their way to avoid using an already treated group as a control. Because if you use an already treated group as a control, it's just kind of like, it's got more assumptions. Yangwan says, but if there's only one treatment date across the years, there's no need to worry about using the traditional. Correct. That's right. So when we have a simple 2x2, the OLS specification that we did up here, the OLS specification up here is fine. Okay, that's totally fine. The problem that we were finding is not the OLS specification. The problem is using an already treated group as a control. But what I was saying is that in differential timing, when you have multiple treatment groups being treated at different points in time, and you estimate that with a regression, the coefficient is going to be a weighted average of a bunch of different diffs, some of which are using already treated groups as a control group. And so the biases that people have been talking about with two-way fixed effects, where is it coming from? What's wrong? Why can't we use two-way fixed effects with differential timing? Because two-way fixed effects with differential timing will use already treated groups as a control. The form of what is being identified with two-way fixed effects is basically this. It's basically that. It's going to be a weighted average of all ATTs, a weighted average of parallel trends minus the changing treatment effects for your comparison from your earlier treated groups. And this is kind of it's kind of interesting that this is not just a differential timing issue. This is a more general issue. Don't use already treated groups as controls. Pedro Santana. I once heard him said this. He said, he's so funny. It is a sin to use an already treated group as a control. It is a sin. And so you can't use it. You can't use it because the assumptions that are needed are just too many, right? Okay. So now let's do the next one. Hold on. I'm going to see if let's see. Savin says, can we think of this assumption as the trend between pre and post for control group is the same as when they're treated or not treated? It's a good question. So if the trend, well, it would be, you'd have to say something probably about the trend in Y1 and the trend in Y0. Oh, there we go. Parallel trend for control group. Need to remember why I'm doing that parallel trend for control group. Yeah, but see, Renz, it's more than that. See, that step is that right there in the Discord, that is in my notes, I guess. I must have had it. Where is that coming from? Oh, that's the Sutva. No, it's not. Where'd you get that? Which page is that? Oh, you did that yourself. Yeah. Okay. But that's great. Okay. But that third term right there, that parallel trend, that's true. Yes. But it doesn't really show you enough information. It doesn't really show you enough information. You need to add in, at that point, you need to add in the Y zeros for the post and the pre, and then you'll see then. I need to look at that, Sabin. I need to see that. That's it. That I'll review. I'll look over that. I kind of like, I'm getting a little, but basically, see, the thing I'm trying to say here is that with diff and diffs, when we talk about trends in diff and diffs, it's a very specific term. Trend in diff and diff terminology is referring to trends in expectation Y0. That's what it's referring to. Changes in Y0. See that third term? That's like the Y0, Y1. And that's not like a true trend. That's I mean, you could say it is, but yeah, it is. That's mathematically right. Exactly. It's mathematically equivalent. I don't think though that third term will showcase though that you have why do you have Y0 post in there twice? Because you added in, oh, because you oh yeah, so look, Sabin, that's right. So then rearrange that third term and you get Y1 post minus Y0 post, that's an ATT, minus Y1 pre minus Y0 pre. That's exactly the same thing. It's the change. Yeah, perfect. Yeah, that's actually, that's perfect. That's it. Yep. Okay. All right. So trend, that's the thing we kind of want to remember. And is that the diff and diff is using trends in Y0 to identify the ATT, because with the ATT, we are missing the Y0s. That's the thing to kind of remember, is like in our case, one group gets treated. All right. And we observe it's Y1. We are missing it's Y0. We therefore use parallel trends to basically project correctly that missing Y0. But see, with an already treated group, we don't have any Y0s. We don't have any. And so it's like a very strange expression, because literally none of the comparison group outcome values are Y0s. And so you've got nothing that can like do the projection for you. So you have to kind of realize what you have to do is you have to work through it, like Sabin did there, which is so pretty. You have to work through it and you have to realize, okay, the only way I can use these Y1s to project to Y0s is if the treatment effects have stopped working or the dynamics are 0. Then I can do it, because then that's as though you're using Y0s. But that the thing that we're always remembering is that what parallel trends is doing is basically it's allowing that, because it's this. Okay, it's time. This is T star. And you basically have for the control, there's a Y0 post, and there's a Y0 pre. So we have this trend in Y0s. And this is Y1 post for our treatment, and this is Y0 pre for our treatment. And so what you're doing is you're basically saying, well, I'm going to use that trend in Y0 to project a counterfactual. And what OLS or any of these will do is they'll always use the projection in Y0 to get to that point, and then that becomes their estimated treatment effect. But see, if you're using an already treated group as a control, then you don't have any Y0s to project. So the only way that you could do the projection is if you basically said there is no treatment effect left for that comparison group, and then it will work, or there's no dynamics, and then it'll work. But it's like, this stuff is all very technical. It's all very technical. Okay. Okay. So I'm going to do one more thing. What happens? This is homework 2. What happens if we lose no anticipation? Okay. Which says this: what if my comparison group is always untreated? Okay. So that means Y equals Y0 for all periods, but my baseline for the treatment group is treated. Y equals Y1 in pre. Then what does diff and diff identify? So we have to go through the whole thing. We have to go through the whole thing again. I don't think this one will take as long, hopefully. Let's look. So we're going to get here. Step 1, write down our expression of diff and diff. expectation YK post minus expectation YK pre, big parentheses, expectation YU post. Saban, that was really good. That was pretty. Expectation YU pre. All right. So we start out using the realized outcome notation, Y. Then we go to our switching equation, step 1, switching equation, switch from Y to potential outcomes, depending on treatment status. It's funny how it's really kind of interesting. The more I've like over the years realized how it's all very simple. So much of causal inference is really, really simple. Realized outcomes, switching equation, get into potential outcomes, rearrange, see what the bias is, see what the parameter is. It's like so often that's it. And then you're like, okay, what do I get if I assume randomization? And then you'll see stuff drop out. What do I do if I assume parallel trends? You'll see stuff drop out. You know, so we're going to do step 1 here. But this is why, like, I really make my students at Baylor go through this because it's very eye-opening. See that? So it's treated. There's our big screw up. Well, we don't know. Actually, here's the deal. We don't know that it's a screw up. Good, Saban. That's great. That's why I was hoping. We don't know this is a screw up. See, this is the thing. A lot of people actually had this conversation with a very good methods guy on my Substack. And he was kind of like, well, yeah, it's like obvious you shouldn't use as your baseline already treated. Your baseline should not be treated. But I was kind of like, well, why is it obvious? What do you mean? And there's like this tendency, I think, for people to kind of have like a folklore kind of hand waving gut assumption, but they don't really know the form of the bias. They don't really know the form of the bias, right? So that's why I go through all this. It's like, I want to know the form of the bias. I want to know precisely what is being identified. All right. And the only way you can do it is to work within this kind of framework of the potential outcomes. You know, don't work inside a regression model. Work inside the basic potential outcomes. Use these switching equation, move around, and then you see what you get. So here we go. Minus expectation Y0U post minus expectation Y0U pre. Okay. All right. So that is not right there. You can already tell that we're not going to end up with parallel trends. You're not going to end up with parallel trends. Because parallel trends is all based on Y zeros. So we're, usually what you're getting with diff and diff is it's going to go Y1, Y0, Y0, Y0. You add in a 0, and then it becomes Y1 minus Y0, ATT, plus 4 Y zeros. And we're not going to get that here. All right. So what we're going to do, though, is we're going to add in, so what I always try to do is I try to get it into a parallel trend. I try to create a parallel trend. So the thing I'm missing is expectation Y0K pre minus expectation Y0K pre. So to really see the biases of diff and diff, you want to try to get everything back into a parallel trend and then see what else is left over. When you do that, first get into the standard first. Yes, exactly. Standard non-parallel trends bias in the 2x2 case. Exactly. That is exactly what Saban says. That's what I try to do too. I try to do that too. So we're missing. So watch what happens here. So we'll rearrange this. Okay. Expectation Y1K post. I'm gonna use this one. No. Oh, you know what? I'm missing two things. You'll see why. So you have to do two things. As Saban said, you know, what I try to do is I try to get it into the standard parallel trends assumption first. And that's right. You also are trying to get it into the ATT also. So we needed both of these. So watch. So here we go. Expectation. So that's this one minus here. Okay. So I'm going to put that in minus expectation Y0K post. All right. So that's an ATT. All right. That's an ATT. So we got that. Okay. I got this minus expectation Y1K pre. And I got this Y0K pre. Let's see. Got to group these things. Let's get the standard. Let's do like what was just said though. Let's go ahead and get our Y0K stuff. So we have Y0K post, Y0K pre, Y0U post, Y0U pre. So we're gonna do this first. Okay. So we'll go plus expectation Y0K post minus expectation Y0K pre. Both of those are counterfactual. See that? Both of those are counterfactual because in the post period you're treated. So group K's, we don't observe Y0 in the post. And in the baseline, it was treated. So we don't observe Y0K in the pre. So here we have that. And then, so then we're going to get this standard. I like that standard parallel trends bias term. So we're going to go this expectation Y0 U post minus expectation Y0 U pre. Okay. So there's that look. So here's that's this, and that's this. All right. So what are we left with? We're left with that term and it's Y1K pre and this term Y0K pre. So let's write that down. So look, this right here, use Saban's is the standard. I love that. Standard parallel trends term. All right. That's our standard parallel trends term. And now we just got to add on this. So look, let's just I'll just kind of, without flipping it around, I'll go minus expectation Y1K pre plus expectation Y0K plus, we have to do that one, plus expectation Y0K free, right? So I'm just going to kind of pull out of this minus expectation Y1K free minus expectation Y0K free. So I'm just going to kind of replace it there so that it's just expressed that way. So notice what you get here. So this is that right there is what? It's an ATT for group K in pre-period. In the pre-period. So it's rewrite it. Diff and diff will identify the ATT plus standard parallel trends bias minus ATT group K. So that's ATT group K in the post pre. which means this. Assume parallel trends equals 0. All right, so let's like go through assumptions right now. Assume parallel trends is 0. Then what does identify without NA? ATT group K in the post minus ATT group K in the pre. So check this out. Under constant treatment effects, if ATTK post equals ATTK pre, diff and diff will equal 0. And that's one. And if under dynamic treatment effects, if ATT post K is larger than ATT pre K, OLS will be the OLS will be less than the true ATT. It'll be too small. If there's dynamic treatment effects, it'll be biased down. And so like, so I actually have a simulation for this one. And I'm going to show it to you. If you go to, see, where did I put it? Here, no anticipation, .do. So I'm going to illustrate this. I'm going to have here 1,000 firms, 25, let's see, 40 states, 25 firms per state, 4 years. Okay, 90, 91, 92, 93. I'm going to say group 1 is the group 1 is the treatment group is in the upper half of our like 1,000 firms. So like I got 500 firms that are going to be treated, 500 not. And I'm going to have 1991 be the correct start date and 1992 be the incorrect start date, right? So let me show you how I do this. So what I've got here is I'm going to have Y0 equal parallel trends. Here's my potential outcomes. That's my error term. Y0 will equal my firm fixed effects plus time plus the error. All right. And so all of the Y0s are growing in the data by they start at some intercept and they go up by 1 plus 0, on average 0. Okay. Then I'm going to have treatment effects. All right. So I've got here constant treatment effects where the treatment effect is a 10 after 1991. And then I'm going to have dynamic treatment effects. It's going to be 10, 20, 30. Right. These are our two cases. So we're going to summarize the deltas. Right. We can see here that if there's constant treatment effects of 10. And if there's dynamics, it's 10 plus 20 plus 30 divided by 3. It'll be 20. Okay. All right. Have our treatment period, our switching equation, our aggregate causal parameters, right? 10 and 20. So we know that under constant treatment effects, the ATT is a 10, and under dynamic treatment effects, 10 plus 20 plus 30, 60 divided by 3, that's 20. So that's the ATT in the post period. And now what I'm going to do is use the correct specification. I'm going to have the post term right here is I'm going to use the correct period as my baseline. I'm going to use 1990 as my baseline. And I'm going to go everything after. All right. So for YC, post robust diff and diff should equal 10. And I get 9.97. And if I have dynamic treatment effects, the diff and diff should, the ATT is a 20, and I find a 19.97, right? But what if I did an incorrect specification? I use as my baseline an already treated group as a control, and that's what I do right here. Okay, so I'm gonna say I'm only gonna use the data from 1991 to 93. So 1991 is gonna be my baseline, well, it's already treated, right? Well, we know from my stuff that if, and I have it right here. So we go down here. We said if the no anticipation violation, it's going to be equal to ATT in the post, not standard parallel trends bias term, minus ATT in the pre. All right. So under constant treatment effects, it should be 10 minus 10, which is a 0. So let's see what we find. 0. And if it is dynamic, then it should be ATT in the post minus ATT in the pre. And it biases it down by 5. Kind of cool, huh? Kind of different. So you can kind of see here, like, that this no anticipation assumption is not trivial. It's, you know, I mean, it's like, it's not as obvious. I don't think it's as like, I mean, it's not as surprising, you know, that you shouldn't use as your baseline an already treated period. Maybe it's not as obvious, but now you kind of know, oh, well, if you do, I know the exact form of the bias. I know the exact form of the bias. And, you know, you can see why this can be an issue. And for some of the estimators that we're going to use, they're going to be really sensitive to this issue, and others won't be. For reasons I'll get into. Okay. All right. So let's go ahead and take a 15-minute break. We'll come back at 10:26. We are, I think now what we're doing is we're going to go to, let me do one thing real quick. No. All right. So you might want to pull most recent stuff. Yeah, I updated the slides. Let's see. But we're going to do covariates.pdf now. I was going to do more falsification stuff, but I think I might just come back to it later. I want to stay on track. So we're going to go now to the covariates.pdf, and we're going to make sure that we're now, oh, okay, Alexander, hold on. Let me see. What would be a way empirically show the truth? Yeah, I don't think there is one. That's what I'm saying, Alexander. I don't even know what you would just, you're going to have to assume it, you know? I think it has I think it's called the no carryover assumption or something like that. I actually haven't kept up a little bit with all the new phraseology that everybody's using, but, you know, I mean, at some level, Alexander, like, you're going to always have to use an already treated group as a control. I mean, imagine you're studying the minimum wage, right? You're studying the minimum wage. You want to know, what is the effect of the minimum wage on employment? How in the world are you going to use a group that's not been treated, right? Like every city in the world, going back to, I mean, I think the first minimum wage is like 1,400 or something. I mean, it's like so everybody has been, quote, treated with a minimum wage. So what you've got to do is you do have to make some assumptions that the treatment effects have, quote, worn off. And you know, that's just something, you know, again, like that part of it, like of trying to kind of give a lot of advice or guidance, on, how do I know that my comparison group that was treated 50 years ago is no longer has like pulsing in it a dynamic treatment effect? How do I know that? And I don't know how you could possibly know that. But it does kind of give you some pause. It does kind of give you some pause that about being really careful about who is your control group. And that's all that this is really trying to say right now, is that, if you use as a control group an already treated group, then it must be that the dynamics are zero or the treatment effect is worn off. And then, like, how can I know that? I don't know. I've literally never, I don't think anyone has devised a test like that. Because you would, if you think about it, Alexander, what would you have to do to know that the treatment effects have worn off? You would have to probably do a diff and diff. You'd probably have to do a diff and diff on the comparison group, do some gigantic event study, and then show that, the treatment effects have stabilized. You don't need them to, like, you don't need the treatment effect to, like, you don't need the wearing off idea. It just needs to be that the delta ATT is zero, which you could have it that either because the treatment effects are the same in every period, in which case it'll cancel out, or they just are zero in every period. Some kind of, like, you called it reverting to the mean, but it's like, it's something like that. It's something like that. Yeah, ideally, Anthony says, so maybe using not yet treated. We're going to see that, Anthony. That is, we're seeing now some of the trickier elements, which is just like, who is your control group, right? And what we said was, well, your control group must satisfy parallel trends, right? Like, your treatment group has a particular counterfactual trend. You need a control group that has the same trend in observable. That already is hard to do. Thank God we have the event study, though. The event study at least has kind of been embraced broadly as, like, one of the key pieces of evidence, along with, though, as we said, these falsifications. They really go hand in hand, in my mind. Very good falsifications and event studies work really well to kind of build the case for parallel trends. But something like my control group's treatment effects have worn off, there's not a test for that. There's not even like a heuristic, the event study is not a true test. It's like, it's just kind of like informal evidence. That's the way I see it. It's like, this is kind of like suggestive evidence, but, just because the trends were zero before doesn't mean that they would have continued to be zero after, right? That's like an added assumption, but it's all we got. It's all we have. That's the thing. You work with what you can. If my treatment moves back to baseline, goes from Y1 to Y0, turn off treatment. Well, the treatment can turn off. Think of it like this. Person goes to med school, and then they get a medical license. Medical license turns on. Then they lose their license. License turned off. Are the treatment effects from the licensing also turned off? And I don't know. So, like, yeah, exactly. So it's like, right. It kind of depends. It just depends, like you could have lasting effects of vaccine mandates, even when governments no longer have vaccine mandates, right? They could turn on or turn off. So, that kind of like I think that's the no carryover assumption. Basically, like, that when it turned off, the treatment effects turned off. That's not, I don't think that's guaranteed, that's not guaranteed either. So I think that I'm leaving it to y'all, you guys, y'all is a Southern way of talking. I'm leaving it to y'all to kind of think through this a little bit, in your own work, because we're kind of at the cutting edge, oddly enough, we're at the cutting edge, even talking about this, about, who is going to be my control group. Who's going to be my control group? And you can sort of see how things like synthetic control sort of became so attractive, because synthetic control is kind of devised in a way to create a control group out of a bunch of control groups that basically do run, not parallel, but run the full trend in the pre-period. And, what's non-inferiority? What does that mean, Reese? Is that from epidemiology? What does that mean? What's non-inferiority mean? Is it like another diff and diff? Oh, that's interesting. Okay, that's cool. I have to think about that. All right, so look here. Let's open this up. We're gonna do covariates. Now, Kyle is currently hard at work, about to upload a covariate problem set thing that we've been working on. We've got like a new one. It's really cool. Working with Kyle is a lot of fun, because over the last 3 years, the mixtape session stuff is like incrementally gotten better and better. And we put it all on the GitHub repository. So it's all like, everything's a public good at mixtape sessions. And there's only 2 club goods, and that's the Discord and the recordings. And then the private good would be the live, So the public good, we just kind of pump out all this stuff, and we ask everybody that teaches on the platform to be like, you got to be okay. It is a little awkward. I do feel a little uncomfortable when I ask them, it's like, are you gonna be okay with like putting all of your slides and all of your problem sets and all of your stuff on GitHub repository? Because, professors like spend a lot of time on this stuff, and they have like, they get, they like understandably want to be sort of like, I don't want to share. I want everything to be a club good. But it's been really fun with Kyle, because Kyle comes from that open science kind of tradition, and I'm not coming at this stuff from open science. I'm kind of coming at it more from this like spirituality about giving away. But we've got this new problem set that we're working on, or a new replication that we're working on with covariates. And so we'll do it at the end of the day. Hopefully it'll be better than the Lalonde one. This is the only one I have right now. Kudos to Kyle. Yes. Kyle and me are the team. It's just us. All right. So including covariates. Let's do it. All right. So there is an assumption in causal inference about, estimating causal effects with covariates, control for stuff, reg Y, treatment, and then like put in X's, right? It's like the most standard thing, like we probably don't even remember. I don't even remember the feeling I got when I learned in econometrics, like controlling for covariates. I don't know if y'all remember it. I think it was probably pretty cool. I think I probably was like pretty enamored with it. But I don't remember it. But I think like, most people don't have a clue what that is. Most people are not social scientists. They've not taken a regression class. They don't know about covariates. They don't have a clue what that's about. They kind of know like probably at like a basic level, but they don't really like, really understand what it's doing inside a linear regression model. But see, like everything you learn in econometrics or stats regression classes, they were always like teaching you about covariates in the context of a linear regression model. So everything you would learn about like exogeneity would be about a regression model. Okay. But causal inference is like more basic. Like it's like actually like fairly basic. Like we just saw it, you know, it's like, here's a bunch of letters, switch from, you know, the letters to the letters with a 1 or a 0, and then like rearrange stuff and then like see what I would have to assume to justify the decisions that I'm about to make, you know, and you could do simple, you know, differences in means. You could do something more complicated. So, the linear regression model, when you would control for covariates, you know, you would usually appeal to exogeneity. All right. But in the context of causal inference, the phraseology is different, and it's not based in econometrics. Causal inference is not based in econometrics. Causal inference is based in the experimental design tradition. And so, and then built on top of that, they began to go into the non-experimental. The statisticians did. And they introduced potential outcomes from the very, very early days. And then Don Rubin just went wild on it all throughout the 70s and the 80s on just being the biggest proselytizer for potential outcomes. So much so that it became called the Rubin causal model. And then it just spread. You know, Reese is in epidemiology. It's like Jamie Robbins and others, like they use it. So it's like very, very common. And in the economics, it gets brought in, potential outcomes gets brought in. Arguably, I mean, you definitely see it early on with Heckman, but it's really with the local average treatment effect, instrumental variables with Josh Angrist and Hito Embens. That's really a turning point, because when potential outcomes got applied to IV, it really did something pretty remarkable. Instrumental variables had always been so closely tied to economics. You would like have supply and demand curves, and you were instrumenting for price using a supply shifter. And it's like, if you weren't in economics, that was all just gobbledygook. But then with Angrist and Embens, it was just like everything was potential outcomes, and it was completely removed from economic theory. And that really just caused it to take off. Maybe. Who knows? I actually don't know if that's true, but that's what Embens says, you know, is that, you know, when potential outcomes got applied to IV, all of a sudden IV belonged to everybody, not just economists, because IV was something economists invented. So covariates, you know, are generally thought with causal inference. If you're trying to solve a causal inference problem with controlling for covariates, it's called unconfoundedness. It basically is a form of randomization. It basically says, conditional on X, the treatment is randomly assigned. Now, it does not technically have to be randomly assigned. The treatment must be assigned in such a way that it is independent of the potential outcomes, which to this day, I really don't know how you could ever do that without randomization. But the point here is that, you know, it's conditional on X. Treatment is assigned to units independently of two things: their outcome in a world we're not treated, their outcome in a world we're treated, and any combination of the two, like the treatment effect. So it's not like, so it's better to think of it as like randomization. And, you know, usually people don't think about controlling for covariates as a form of randomizing, but it is. It means that within the dimensions of the covariates, Asian males age 45, treatment is assigned to them independent of their potential outcomes or any combination. And it's the basis for running regressions with covariates, even though running regressions with covariates is usually expressed using the term exogeneity. Yes, I think so. I think that's right. Reese is kind of bringing up, you're being my translator back to epidemiology. For some reason, for reasons I do not really understand, even though this is all rooted in the same, you know, potential outcomes, epi and stats and economics just kind of like evolved where they like talk about the same things using different words. And it's, you know, so it's a lot simpler to go back and forth between epi and like econ than it is to go from causal inference to econometrics, because in econometrics, you're usually already living inside a particular model, and potential outcomes has no model. There's no model at all. It's like, Y1, Y0. That's it. So anyway, we usually motivate controlling for things as we usually motivate this assumption of putting in controls, putting in covariates with diff and diff, but it's technically like a little bit different. It's technically a little bit different. You're not in diff and diff assuming randomization. Okay. That's what we're going to see. Exactly. I'm going to put that up. So what Wei said, if we care about if diff and diff requires parallel trends and not strict exogeneity, if it requires parallel trends, why do we care about covariates? Exactly. And you have just said it, Wei, because sometimes parallel trends fails, but can be corrected with covariates. That's the reason. That is the reason for putting in controls. The inclusion of covariates in diff and diff models, yeah, it can improve the inference, but we're going to see, Waldo, that it's that we'll come back to that. It can improve the inference under certain assumptions, all right, that we're going to talk about. So the inclusion of the covariates in the diff and diff models is not about trying to find random variation in the treatment within the values of X, okay? It's basically what Wei said. It's based on the claim that the parallel trend assumption has failed, but with the inclusion of the covariates, it can be recovered. It's all about they're using matching. It's deep, Anna. It's deep stuff. I don't quite like know the formalism, but I think you're absolutely right. Anna said, and that might also explain why some people use matching in diff and diff, right? Because with this matching approach, trying to find units that on covariates are observationally equivalent. And I think the next step is, since they're observationally equivalent, parallel trends would hold for them. Treatment groups are small. It's a good question, Nora. I'm going to think about that. Let's stagger diff and diff. Well, okay, that's a lot to answer. We'll come back to that, Wenjing. All right. Let's first start with covariates, not fixed effects. Even if you put in the fixed effects, I'm not completely I mean, that's a good question. I'll have to think about that, because I'm used to thinking right now in terms of this particular formalism of the covariates, and I need to think if that would be the case, because it's what's happening here is that it's basically what we're going to be doing. Oh, and Anna, so, you said, and this might also explain why some people use matching in diff and diff. It's like what we're kind of realizing is that the reason why you use covariates in a cross-section regression is to recover randomization. The reason why you use it in diff and diff is to recover parallel trends. And the reason you use it in synthetic control is like a completely different reason too. So, probably, Anna, I would say, yes, that is, you're right. That why people use matching in diff and diff is they're basically probably saying that since they are similar on observable characteristics, which is what matching would be. I've got some propensity score and I've got like a 0.7, and then this guy in the control group's got a 0.72. I'm gonna match them to each other. Then what you're then saying is that the parallel trends assumption would therefore hold for them. That's another step, and I don't actually know if that's that. I don't actually know how to think about that. That might be, but you might be right. So, ATT. I like to always write things down very simple. So we write down the ATT. ATT is expectation delta for the treatment group. Expectation Y1 minus Y0 for the treatment group. I put the Y0 there because it's missing. ATT is expectation Y1 for the treatment group minus expectation Y0 for the treatment group. That's missing. Use the switching equation. Expectation Y for the treatment group minus expectation Y0 for the treatment group. So what you see here with this expression of the ATT is that the only information that we're missing is this. Part of what we need to calculate the ATT is the average Y for the treatment group, and we have that data. If you are in the treatment group, the outcomes that I observe are Y1. So there's nothing wrong with the data that I have for my treatment group. I just am missing Y0 for my treatment group. All right. And so we use parallel trends to basically impute it. That's basically what's going on. All right, so this conditional parallel trends is what we're going to get into. So the diff and diff equation is, this is diff and diff equation. And then we went through all that stuff and we get ATT plus non-parallel trends bias, or what Sabin was calling the standard parallel trends expression. Everything's expressed in terms of Y0s. Okay. And if we believe that parallel trends fails, all right, then diff and diff will not identify the ATT, right? Because diff and diff is always equal to ATT plus this bias term. And so if that bias term is not zero, then diff and diff is going to be the sum of the causal effect and the bias. But what if you believe that conditional on covariates, parallel trends holds? Just doesn't hold in aggregate, but it holds within the values of X. So like men have parallel trends, women have parallel trends. But if you don't put but like parallel trends doesn't hold for the group, maybe because they have different trends. And like, might be like, because of some different composition of men and women in the treatment group and the control group, parallel trends will not hold in the aggregate for the treatment and control, but would hold like within the groups. Okay. So there are methods we can use that will incorporate covariates into the diff and diff equation such that this goes to zero. All right. But it's not straightforward. All right. So the inclusion of covariates will have a particular regression specification that's not the one we normally run. And the inclusion of covariates, and then there's alternative methods that we can use too. And so we're going to review all of them. So we're going to look at inverse probability weighting, outcome regression, doubly robust, two-way fixed effects. It's going to be the day. All right, so there's 3 papers. We're going to go slow, going to go deep. I have a reject and resubmit at the Journal of Economic Literature with Pedro Santana, Andrew Goodman-Bacon, Brantley Calloway, and Andrew Baker on diff and diff. Now, it's a lot about covariates. And we're going to talk about 3 papers. And when I've had Brant Calloway teach, he teaches his stuff. I just can't cover it all in the basic diff and diff. Because as you can tell, the basic diff and diff gets pretty deep itself. So there's only so much room I can do. So 3 papers about covariate adjustment in diff and diff. Alberto Abade's 2005 restud on semi-parametric diff and diff. What it's going to do is, since we are missing this Y0 for the control group, but just real quick, I'll just say this. Causal inference is always going to be about some missing potential outcome. And what you're going to try to be asking yourself is, all right, I'm missing that potential outcome, but I have Y0s for the control group. When can I use the Y0s from the control group to be my Y0 for the treatment group? I can look into that. Yeah, Camille, that's probably worth me just sort of I used to know that stuff pretty well. Yeah, I'll think about that. Let me write that down. Yeah, it's like, yeah, I forgot about that. That would be a good thing to do. All right, so here we go. So we're missing Y0 for the treatment group, but we got a bunch of Y0s for the control group. So maybe we can use them, right? And so what Abbott's going to do is Abbott's going to use the Y0s for the control group in a diff and adjust them with a propensity score. He's going to reweight the comparison group part of the diff equation, which is right here. He's going to reweight that with a propensity score based on X. Heckman, Ickamer, and Todd, they are not going to do that. What they are going to do is they're going to impute Y0s for the treatment group and control group. They're going to impute Y0s for the treatment group and the control group using the covariates at the baseline for the control group. They're going to like look at the change in Y0 for the control group based on covariates, and they're going to use that relationship under parallel trends, use that relationship between Y0 in the pre and Y0 on the post based on the covariates to then impute what the missing counterfactual would have been for the treatment group, right? And then Pedro Santana and Bean Zhao, they do what's called double robust. Double robust is basically always some form of do it using propensity scores, do it using an outcome regression model, but do it at the same time and do it in such a way that, you only have to get it right once, right? So he's going to look at both those. And then we're going to discuss all three of them. Okay. We're going to discuss all three of them and we're going to compare it. No, it's not, Winchin. Propensity score is not identical with matching. Propensity scores are just a way of reducing the dimensions of the covariates into one dimension, a conditional probability of treatment. You can use it with matching, and that's traditionally what was done. You can also use it with weighting, which is what has been proposed also, inverse probability weighting. You can also use subclassification. There's all kinds of ways to use the propensity score. So this is not going to be matching. This is not going to be matching. This is not going to be the stuff that Anna was talking about at all. This is going to be weighting approaches. Okay. Invert, it's going to reweight the comparison group by the propensity score. And then we're going to compare all of it with two-way fixed effects. We're going to see how they all perform. All right. So this is a semi-parametric difference in differences paper in the 2005 Review of Economic Studies. And here's the basic idea. All right, here's the basic idea. He's going to propose a model that simply reweights the control group in the diff and diff using the propensity score, but it's called semi-parametric diff and diff because he's going to require this like series expansion on the propensity score. Because the thing about propensity scores is it's a model, okay, where you take the covariates, you estimate a model, and then you predict probability of treatment based on the covariates. But it's a little bit more subtle than that because it's not just based on the covariates, it's based on the modeling of the covariates. So it'll be like, it'll be something as simple like, did you use a logit or a probit? That's one way. But it's also like, did you use age or did you use age squared? Or did you use age squared and age cubed? Or did you use age interacted with income? Or did you use age interacted with income and income squared? It's like, your basic, it's a very formalized parametric approach. Okay. And, so he's going to propose a particular form to that propensity score. that like is called the semi-parametric approach. And so it's going to be a particular specification. And, but he's going to estimate the propensity score based off the pre-treatment characteristics, pre-treatment covariates. And you're going to start to see now, I'm just going to give you a little heads up. You're going to start to see now that with this covariate stuff in diff and diff, because diff and diff is longitudinal, right? It's like over time, pre to post. When you run a regression with covariates and you put in like fixed effects, it deletes. It will delete anything that doesn't change over time, right? So the only time you really can ever put covariates in a two-way fixed effects, model is if they change. If you've got time varying covariates, covariate in the baseline is one thing, covariate in the second period is a different number, right? All of these models here, Abity, Heckman, Santana, and Zhao, as well as Callaway and Santana, are going to use just the covariates at the baseline, because this is part of where it's kind of jarring for a lot of people. They think of controlling for stuff about controlling for omitted variable bias in each period, right? Like that's the way most people typically think about covariates. They think of it as, well, I've got omitted variable bias if I don't put this in. So I got to put this in and so it's got to be, the variable's got to be there in every period. But see, remember what we said. We said that is one of the things that makes what you're doing with diff and diff different. You're not trying to control for omitted variable bias. You are trying to, kind of getting back to what Wei said. You're not trying to get to this isn't about strict exogeneity. This is about parallel trends. You're trying to recover the parallel trends assumption. Well, what is parallel trends? Parallel trends is Y0 in the pre to Y0 in the post, right? So it's all about a change in Y0 from pre to post. And you're going to use the change in Y0 from pre to post in the control group to basically fix the parallel trends assumption itself. All right. So you're not going to be using the covariate values in the post-treatment period for this. You're going to be using baseline. You're using baseline covariates. You're going to estimate the conditional probability of treatment based on the baseline covariates. That's going to be a propensity score. Well, first step you're going to do is you're going to calculate for every unit the change in the outcome. How did it change over time? Which is, again, that's what this is. Change in the outcome, change in the outcome, right? So this is just like the averaging, but everybody's being calculated change in the outcome. So you're going to do that, change in the outcome, each unit's after minus before. Then you're going to estimate a conditional probability of treatment based on baseline covariates, and then you're going to weight the comparison groups, diff and diff equation. Exactly. Alexander's just in there helping out. Thank you. So weight the comparison groups, diff and diff equation with the propensity score. Remember, this is the thing though. ATT is only missing the Y0. That's the part that's broken. So that's the part we focus on. You're just going to use D equals 0. You're going to use their Y0s. You're going to use the control group's Y0s to impute this using the covariates. You're going to weight the comparison groups, diff and diff equation with the propensity score, because there is nothing wrong with this one. What's wrong is like, your comparison group. All right. So novel elements of time. There's only one treatment group. Abity's model does not work with differential timing. This was it's one of the only econometric papers before all this wave of differential timing. There was really only a couple of econometric papers on diff and diff. There was Heckman, Ickemer, and Todd, 1997, which we're going to discuss, and Abity, 2005. There is that Bertrand, Duflo, and Mullinthan Should I trust Diff and Diff? But it's like, it's all about, it's not about the point. It's not about biased point estimates. It's about, biased standard errors. And so this one, and it really was, it's still used like two-way fixed effects. So this is like, these are the novel elements. So first, only one treatment group. All right. Since we're only using it still in a world of the quote 2x2. Period prior to treatment is going to be called the baseline. We've already been doing that. Or the B period. I use his notation. So it's when treatments, it was with the treated units were not treated. Okay. XB are baseline covariates. It's the value of the covariates in the pre-treatment period at baseline for either the treated or the comparison group. Propensity scores only going to be estimated off the baseline period only. Abity throws away covariates after the treatment because this is all about reestablishing parallel trends. And parallel trends is a baseline concept. It's all about pre to post. So it starts at pre, goes to post, right? Okay, let's take a 15-minute break. Let's take a 15-minute break. We'll come right back at 11:20. So Kyle is at 4 o'clock. Kyle Butts at 4 o'clock. He's going to take us through this new, he just posted it. So you're going to need to pull, need to repull, but he's going to take us through this cool new assignment that he's been working on, and he's got it done now. And, in it is, a covariate, diff and diff to diff and diff, outcome regression, inverse probability weighting, doubly robust. Okay, so that's the stuff we're covering today. And I wanted to kind of give you an explanation of, he's going to do it at 4 o'clock Central Time, but I wanted to give you an explanation of why, what it sounds like when you believe parallel trends won't hold and why you think it might hold with covariates. So he says, this exercise is going to work with data from Khaing and Moretti 2014. This paper aims to analyze the impacts of the Tennessee Valley Authority on local agriculture and manufacturing employment. TVA was a huge federal spending program in the 1940s that aimed at electrification of the region, building hundreds of large dams, in Scott's terms, a ton of bytes. Region was centered in Tennessee, surrounding other southern states. The region had a large agriculture industry, very little manufacturing. Electrification brought in a lot of industry, moving the economy away from agriculture. We're going to test for this in the data using census data recorded every 10 years. I'm from Tennessee. I'm actually from Mississippi, but I went to high school in Memphis, which is like over here, and I went to college over here. So these I'm familiar with these dams. So here we go. Moretti and Khaing were nervous that the parallel trends assumption is a bit strong in this context. Why might that be in the context of the Tennessee Valley Authority? Why might it be that you believe parallel trends is not plausible in this situation? The answer is TVA was built in the Tennessee area precisely because the area was not developing a strong manufacturing base. It is unlikely, in the absence of treatment, that counties in this area were going to grow in manufacturing the same as the outside counties, right? So it's like, so you can sort of see here, it's like, it was a targeted treatment at areas that had low manufacturing. The control group are areas that have high manufacturing. So it's very unlikely that had they not built the TVA, that the outcomes would have continued to grow in both at the same rate. So what they're going to do is they're going to incorporate in these covariates. I don't exactly know what model they do, but that's what they're going to do. So 3 main assumptions, conditional parallel trends. Now remember, bundled inside conditional parallel trends is no anticipation, Sutva, right? So you can't have I mean, I probably almost now think I should just write them always down. But anyway, conditional parallel trends and no anticipation. I'm going to write that down. So, okay. Conditional parallel trends. That's what they call it. And you know what? Actually, I'm going to put this up real quick. So if you go back to yesterday's lecture where I went through the three waves of diff and diff right here. I said, the identification shifted away from strict exogeneity. I said early identification by Blundell was always based on strict exogeneity. And this was viewed as too strong by Athey and Evans because you didn't need all of that. You don't need exogeneity to get it. You can just use parallel trends. Heckman, Jim Heckman, Petra Todd, Hide Ikamura, in their 1997 article, they introduce the potential outcomes notation for parallel trends, but explicitly they use conditional parallel trends. They say, because that paper was all about covariates. So it's term D, blah, blah, blah. Term D is like some diff and diff equation. Identifies the average treated and the treated, conditional on X for the treatment group if the following assumption holds. And here we have a conditional parallel trends assumption, which is to say that units that are similar in X, treatment and control, would have had similar evolution. There it is. That's the conditional parallel trends assumption. Comes up 2005, 97, 8 years later. 8 years later, but there it is. That's what we're assuming, that units that are similar on X have parallel trends. Units that are not similar on X do not. They don't have to. All right. We just need it to be that, 4 units with those values of X, they would be similar. But anytime you introduce covariates into these kind of non-parametric or these kind of, less parametric approaches, non-regression based approaches, anytime you incorporate covariates in order to establish something like that, and you say something like treatment group and control group with similar characteristics, you need the characteristics to exist in both treatment and control. So if you're saying something like, manufacturing, some counties that are similar in the treatment and control group, such that you reestablish this like trend, it's got to be that those characteristics are in the treatment and control group. That's called common support. Regressions don't need. Yes. Thank you. Yep. Thank you. In fact, I'm going to do it right now. All right, sorry. So we throw away those observations with no common support. No, inverse probability weighting is, well, these papers do not give guidance, Anna, on that. Probably what I would say is, inverse probability weighting and outcome regression you might want to have to, well, outcome regression will not have any will not have it. And, yeah, so you throw it away. You can trim, you can definitely trim, but literally none of the papers, will give you, the Abity doesn't really give you any guidance on it, and neither does Pedro. So I hesitate to say what I would recommend. But if you do not have common support, you cannot, it's one of the assumptions. So if you don't have common support, you're going to probably have to trim in order to reestablish it. But probably so. You're definitely going to want to check, right? So here's the 5 main assumptions: no anticipation, Sattva, we did that, conditional parallel trends, common support, and here's a big one, that the propensity score is properly specified. So propensity scores are not synonymous with matching. Don't think of propensity score. When you think of propensity score, do not think of matching. When you think of propensity score, think of collapsing. What you're doing is you are taking some large matrix of covariates, okay, and you're just simply, that has some huge number of dimensions, and you're just collapsing it into one dimension, and that one dimension is the propensity score. Okay, so dimensions are not the same as covariates. If you have continuous X, then you have infinite dimensions. Covariates, dimensions mean, every stratification. So if you have like race, sex, age, right? The dimension would be white male, 47-year-old. Okay. White male, 48-year-old. That's the second dimension. White male, 49-year-old. That's a third dimension. And you go through, it depends on how many ages you have, how many sex values you have, and how many races you have. You can go through and you can calculate how big the dimension gets, and it gets really big. It can get very large. And so lots of times, kind of what Anna was saying, you'll have observations that don't have common support. You end up with a data set that is basically too small relative to the dimensions, because sometimes the dimensions can get up into the millions. And like I said, with a continuous covariate, then the treatment group will not have, the treatment group will have a value of that continuous covariate, and that value will not exist in the control group, because by definition, it can't. With a probability that you find, the probability that any two data sets are going to have the exact same value of X when it's continuous is 0. So, so propensity scores are about reducing the dimension, and then you use them. Yeah, there's always things you can do with that. There's a method called coarsened exact matching. That's kind of what they do. They bend the variables, and then they do matching they do exact matching within the bins. It's, you can always do these things. They just technically are not, they kind of are like, we're not doing this, but like, you can bend things, then you're gonna have to make assumptions about the treatment effects within the bins, that they like are homogeneous within the bins. But yeah, there's always things like that you can do. So think of common support like exact matches, right? I'm a white male 47, I'm a white male 48 years old with a PhD. Can I find a white male 48 years old without a PhD? It depends on the data set, but the data set you can imagine that some data sets, if I have to match on race, sex, age, and common support means I got to find somebody exactly like me, observationally exactly like me in the control group. And, in an infinitely large data set, you'll find it. In a finite data set, you won't. I mean, common support basically never holds. So propensity score theorem is by Paul Rosenbaum, Don Rubin, 1983. It's published in Biometrica. It's the second most cited paper at Biometrica. and has like 30,000 sites or something like that, 40,000 sites, grows every single year. It's a very influential paper. They showed that if you need X to satisfy some assumption, then you can turn X into the propensity score, and the propensity score will satisfy that assumption. Okay, so basically propensity scores are really convenient for taking something that's gigantic and turning it into one thing. You still have to estimate the propensity score because you don't know it. Only people that are doing lab experiments know the true propensity score. If they're like if they're like, they've got some dice they roll, and they're like, if you're a male, then, any even dice, you're going to get the treatment. But if you're a female, then it's going to be only if it's the dice roll is above a 9, right? They know that because they set that, but the rest of us don't know what the true propensity score is. So you have to estimate it. And that's where Abity is going to kind of provide some guidance. So common support. All right. So since we're identifying the ATT and the ATT is missing Y0 for the treated group, we're going to use the control group. We're going to use the control group because the control group is filled with Y0s. They're just not the Y0s of the treatment group, but we're going to use them. And under conditional parallel trends, we can kind of use those observations with covariates that are comparable to the treatment group to basically adjust the control groups, to adjust the control group's average Y0 such that they can be a substitution for the treatment, the missing counterfactuals. This is the kind of stuff Anna was talking about with matching, but it's not going to be matching. But it's kind of similar idea, right? This is common support. I need to probably update this, but here you see like a propensity score. Propensity scores are going to be bounded between 0 and 1 because they're probabilities. So, they're going to go from 0 to 1. And always what goes on in a non-experimental data set, the treatment group will have propensity scores that are on average larger than the propensity scores in the control group, because if these covariates were the reason that people got into the treatment, then, you're probably going to have more of them in the treatment group than you have in the control group. And so you'll usually get this different distribution, right? So common support, basically, it's like, here's the distribution of the propensity score for the treatment group. Here's the distribution of the propensity score for the control group. Common support universally would mean that, all ranges, well, like roughly speaking, all ranges where I have propensity scores similar to one another in the treatment group and the control group, that would only be right here. That's the only part where I have common support. And that's because if you look closely, the treatment group only goes to right there, right? So even though I have some control group propensity scores that are lower, treatment group only goes there. So that basically means I don't have support over here and I don't have support over here. All right. Well, so what we are dealing with the average treatment on the treated common support is we need to take our propensity scores for the treatment group and we just need support for the region associated with the treatment group. So like, I don't care that I don't have treatment group units to go with these control group units, because for the ATT, I'm just trying to find substitutes for the treatment group, and the treatment group only goes from here to here. So basically, I'm just focused on this part. Okay, I'm just focused on that part. And so you can see right here, I am missing support for these guys. I don't have anybody in the control group who has a propensity score that high. The largest the propensity score ever gets for the control group is right there. So I do not have support for this region. So to Anna's question, what do? Do you just throw them away? That's one thing you can do. That's one thing you can do. So we define the ATT. So look, the ATT is expectation Y1 minus Y0 in the T period, meaning the post for the treatment group. Expectation Y1 for the treatment group in the post period minus expectation Y0 in the post period for the treatment group. We're missing that. We're going to estimate it with Abadi's inverse probability weighting estimator, which is going to be this whole thing. It's going to be an average reweighting of the change in the outcome. All right. So look, let's just put this in here. That's the propensity score, right? That's the propensity score. All right. Let's say that you're going to reweight everything. This right here is not a propensity score. It's just the share of the units that are in the treatment group. Everybody's getting, it's a constant. Everybody gets the same, like it has, everybody's getting the same, that constant is just going to move outside the expectation operator. And it's not a weighting that's unique to anyone. It's going to be a weight over the whole expectation. Okay. Put that aside. So here's the first difference, right? After minus before, it's like a, it's like a time series before and after, right? From the baseline, weighted by this weight. This is the whole thing is a weight. All right. So if you're in the treatment group, right, it's D, which is a dummy, minus the propensity score divided by 1 minus the propensity score. Right. So if you're in the treatment group, that's a 1. 1 minus propensity score divided by 1 minus propensity score is a 1. So you do not weight. Number 1, you don't weight the treatment group by the propensity score. Because remember, nothing is wrong with the treatment group observed data. It's the treatment group's missing counterfactual data that we are worried about. Okay? That's what we're worried about. So you don't, since we have Y1 for the treatment group, we do not weight them. Those are perfectly legitimate. It's this part that we're missing. Okay, it's that part that we're missing. And so we have to weight that. So what if you're in the control group? What's the weight on the control group? The control group is the only group that is getting weighted by the propensity score. And they're being weighted by the inverse of the propensity score. Negative p-score divided by 1 minus p-score. That's it. All right. So the minus, people always are like, where's this minus coming from? Where's this minus coming from? Why are we doing a minus? Because like the thing is, what's going on is like, imagine you've got this like column of YT minus YB. Got a column of that number. It's like a column of numbers. Number 1 might be a 10. They're in the treatment group. Number 2 might be a 15. They're in the treatment group. Number 3 might be a 40, 50. They're in the control group. And number 4 might be a 5 and they're in the control group. All right. So you've got this column here of numbers of this. Each of them will be weighted by something. So this will be weighted by a 1. This will be weighted by a 1. And this will be weighted by negative p-score 1 minus p-score. And this will be weighted by p-score 1 minus p-score. And all you're going to do is once you do all of this, you're just going to take, a weighted average of the entire column. And that's IPW estimator. That's all it is. Okay. So why are you doing this negative? Why is this negative there? Because of that negative. You're going to subtract out, these are going to add together divided by the number of units. So this negative here is driving that negative there. All right. So let's say that Anna has Anna's p-score is 0.1. 10% of the people who look like Anna on X are in the treatment group in our data. That's all it means. Okay. People that look like Anna, 10% of the time, they're in the treatment group. 90% of the time, they're in the control group. Right. So what is her weight? What is Anna's IPW weight? It's going to be, put the negative aside for now. Let's just do this. 0.1 divided by 0.9. 1/9. You're going to multiply her, YT minus YB by 1/9. It's shrinking it. It's shrinking her contribution to the final calculation, right? Okay. What about Caber? Caber has a propensity score. Hey, Kyle. Caber has a propensity, Kyle's here, has a propensity score of 0.9. Okay. Caber's IPW weight will be 0.9 divided by 0.1, which is 9. It'll go Caber's YT minus YB number multiplied by 9. Caber's contribution to the final calculation is 9 times larger than a treatment group unit, which is 1, right? Okay, so individuals with high propensity scores are getting weighted up. Individuals with low propensity scores are getting weighted down, right? And that's the basic idea. All right. So that's the first thing. Very simple estimator. It's got tons of proofs and stuff, but that's the idea. It's common to hear people say, we don't know the propensity score. We can only estimate it. Same here. We don't know the propensity score. We don't know that number for each person, that number, because, you're not really, you know it for X's, but you don't really know like how those X's are working together. So he's going to propose doing a kind of series. He calls it a series logit, and he's going to impose structure on the polynomials that are used in the propensity score. It's his 4th most cited paper. I printed this is even more now. It's definitely it's 4th most cited paper. It's very, after his synthetic control papers, and I guess something else I don't remember. So, but that's the basic model. That's the basic model. And it's incredible how influential the paper's been. It's got 2,300 sites. It's incredible that it's got that many sites. Given I've literally never seen anybody use this estimator my entire life. A lot of the times the econometricians are talking to each other and not necessarily getting adopted in the applied community. And I don't know of anybody that really used it. So I don't really know exactly the history of this paper, but it's now getting used a lot. Okay. Because it's inside all these new diff and diff models. So secondly is this outcome regression paper. This is by Heckman, Ikamura, and Todd. It's also been very influential. It's Heckman's 2nd most cited paper, incredibly enough, after his, Hackett sample selection paper. And it's Petra Todd's and Hide Ikamura's most cited paper. So it probably now has 10,000 sites. So, and then there's the doubly robust. And the doubly robust does both of them. It's Pedro's 2nd most cited paper, at least it was. So the doubly robust model will control for the covariates 2 times. Once using Abade's method. Second time using Heckman's method. It's going to do it both in the same expression. It's going to have an outcome regression model. Outcome regression is not the same thing as just regression. Okay, so it's a little bit different. It's an imputation model. All right. And so you're going to be imputing missing counterfactuals using a regression approach. And so that regression model must be correctly specified. No, it doesn't. It's not that easy, Winchin. You've got to literally do a reweighting. You don't put it in as a control variable. Regressions kind of do their own thing, so it's not as simple as just putting it in. It's like once you start working within the world of the regression, it adds in some additional kinds of assumptions. So even then it would, probably you could do it maybe if you like fully saturated or something. I'm not even positive then. But you're going to use it. You're going to, well, it would probably reestablish parallel trends, but it won't address some of this other stuff that we're going to talk about. Plus, the propensity score is being estimated off of the baseline covariate, so it doesn't change over time. So when you put in any fixed effects, it's going to delete it. So there's all kinds of reasons in the diff and diff it won't work to do it like that because it won't change over time. It's just going to be the baseline propensity score. So so you're going to reestablish parallel trends, using that reweighting method. You're saying, but it won't change over time. So if there's any kind of fixed effects that are put in, it could delete it. Okay. All right. We've got 9 minutes before 12, but if we start diving into this paper, we won't get very far in 9 minutes. So let's just go ahead and take an early lunch. We'll come back at let's take a little, get an extra time. We'll go 1 hour, 9 minutes. We'll come back at 1 o'clock. Okay. And then we'll pick up the doubly robust, and Kyle's going to take over at 4. So let's go ahead and stop now. We'll be back in a little bit. Okay, I'm reading some of this. Kyle's offering a lot of great commentary. Okay, there's lots of good stuff in here. Oh, and there's some stuff. United versus Liverpool. Okay. All right. So where were we? Okay. Yep. So we'll go for an hour and we'll try to see if we can make a big dent in this. I think we're going to be fine. I think we're on target to basically be setting up Kyle for his replication of the the Klein and Moretti paper. Sorry. All right. So doubly robust. All right. So we're just going to dive directly into the doubly robust. This paper right here by Heckman, Ikamura, and Todd, it's actually it's very long and it's very difficult. And so we're going to just kind of discuss this outcome regression paper in the context of the doubly robust paper, because the doubly robust paper is going to do simultaneously Heckman's model and Abady's model at the same time. And that's what doubly robust does. Doubly robust does 2 ways of estimating these treatment effects. Like there'll be 2 ways to do it. They'll be like use the propensity scores, but the propensity scores have to be correctly estimated. And that's according to a model, or do this outcome regression, but the outcomes have to be estimated according to a particular model. Either one of them is unbiased if you have the model right. So which one do you do? And both of them are biased if you have the model wrong. So which one do you do? And doubly robust, what the doubly robust estimators, the class of estimators do in general, is they basically do both of the methods at the same time. They do both of the methods at the same time. And then use those, but then only you do both of the methods at the same time in a particular way. controlling for the covariates twice. But you only have to get one of those models right. You can get the other model wrong and it won't penalize you. So rather than having to pick between, should I use Abity or should I use Heckman, the doubly robust says, let's do both of them. Let's do both of them at the same time. And if one of them's wrong, but the other one's right, it won't matter. It always sort of like, goes towards the one that's right. So of course, if they're both wrong, then it doesn't help. So the other thing is the doubly robust is something that you need to know about, even if you think you're not going to use it in your studies. It is inside the Callaway and Santana differential timing paper that is one of the most common. It's one of the most common at differential timing methods. So is the doubly robust still just another way? Well, it's not. It is. Well, no, not. I guess not exactly, Harsha. This propensity score of Abity's right here, it could be incorrectly estimated and conditional parallel trends still holds. So like, if you go back to the assumptions here, conditional parallel trends is like totally separate from was the model properly specified. And so you can have parallel trends, conditional parallel trends, and still have a biased method if you're using Abity's model and you do not correctly calculate the propensity score. So what doubly robust is doing is it's basically saying, well, look, I'm going to assume all four of these are holding. I just don't know about this one. Okay. And so doubly robust is going to say, all right, you don't know if you have the right propensity score model, and you don't know you have the right outcome regression model, but you do know that you have parallel trends, conditional parallel trends. I'll just do both. And, it will lean towards the one that is properly specified. Okay, it'll lean towards it that's properly specified. So, okay, so there's a couple of different deals. The data, you have to have panel or repeated cross-section data. If you're working with cross-sections, you can't have that issue of the changing sample compositions where the samples have changing Y zeros. Okay, that's what we said. Conditional parallel trends, again, common support. All right, so these three, and I guess we should include no anticipation here, Sutva there, right? So like, I'm still struggling a little bit to know, do you say Sutva, no anticipation, parallel trends? Because if you say parallel trends, there's no anticipation and there's Sutva, but we already saw that you can lose no anticipation, do a bunch of manipulation, and, pull out a standard parallel trends assumption, but like it'll be filled with all these counterfactuals. So probably I do need to add in here, you're still going to need no anticipation. You're still going to need Sutva, right? So that I'll have to change. But anyway, so you have conditional parallel trends. Common support. It's got to be that there's units in the treatment group and the control group with those covariates that are needed to reestablish parallel trends. With those, that says 3, but I guess with those assumptions, including Sutva and no anticipation, then we have a couple of options for estimating the diff and diff model to estimate the ATT using diff and diff. You can either use outcome regression, you can use Abity. Outcome regression, we'll call it OR. Abity, we'll call it IPW. So this is going to require its own correct model, and this is going to require its own correct model. And when I say model, I mean, it's like a propensity score. The propensity score model, it's going to be something like logit, treatment X, X1, X2, ... predict p-score. And then the outcome regression model will be, y, it'll be delta y regressed onto, it'll be delta y0 regressed onto X1, X2 for the control only, predict delta y0 for everyone, or for the treatment group, right? So like both of them, we'll look at this a little bit more, but like both of them have a model, is my point. Both of them have a model. Logit, do you have the correct covariate specified? Outcome regression model, do you have the covariates correctly specified? If you have conditional parallel trends, no anticipation, SUTVA, common support, if you have those things, all right, but you do not have the correct model, it won't work. So they both have their own models, right? Yeah, Sanchita. So there's things that you should do. I was just talking with Pedro. So one of the things you can do is there's a particular normalization of the propensity score weights that you can do. I talk about it in the book. I think it's called, I can't remember if it's the Hasjic normalization or if it's this Horvitz. Anyway, they both start with H, so I forget. But anyway, there's a particular normalization you can do when you do not have very good common support, and it can create stability. But if you do not have common support, even that normalization will not solve it. It can create stability, but it won't like address the unbiasedness necessarily. It can like limit it. It can like make it less severe. But what is recommended by Hito Embens and Rudder, and then somebody else, is to drop observations with a propensity score above 0.9. If you don't have common support, just do it like that. Don't make any other adjustments. That's for the different, that's for the ATT. For the average treatment effect, you would do anything below 0.1 and anything above 0.9. You would just shave off the tails. Now, the only reason I'm hesitating a little bit, Sanchita, is that anytime you start dropping observations in order to satisfy common support, you are no longer estimating the same parameter, because your parameter was the average treatment on the treated, and you were estimating counterfactuals for the treated units. And if you just dropped a bunch of treated units, it's no longer the ATT. So it's something for you to just kind of wrestle with a little bit, which is, you could be trading one bias for another. And so I don't have great advice other than to point you to that Embens paper and to say, if you're going to do anything, trim at 0.9. That's the best I got. I'm reading Yinju's. Wouldn't you still have parallel trends but violate no anticipation? Yeah, Yinju, but remember how we in order to get like when we did through that whole thing without no anticipation, we had to like go in and like add in a bunch of zeros like 3 times or something. And then we were able to recover the ATT, a new parallel trends assumption, which was like, had even more counterfactuals in it. And then we had that, minus the baseline ATT. And so 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 like you can always, you'll still have a parallel trends is my point. You'll still have a parallel trends. It's just that you'll have other stuff if you violate no anticipation. So I'm always just trying to figure out, does that mean, so I guess I do need to list no anticipation in SUDFA. I guess that's where I'm going. Now if anticipation, yeah, so, well, anticipation does not change the Y0. It makes the baseline treated, which is not to say that it's changing the Y0. It means that the baseline is Y1, not Y0. So it's not saying it's changing Y0. It's just saying that I am treated because of my expectation of the future treated period. I am now treated, or, my baseline is just treated. That's like another way of saying it. I mean, another way, basically the way of saying it, honestly, no anticipation, the word no anticipation has too much behavioral baggage. All that no anticipation means is baseline is untreated, period. For whatever reason, baseline is untreated. You can go through all this stuff. Does it require a behavioral theory about rational expectations? No. You could literally have set up the data wrong and you have at baseline a treated unit, right? So it's like, it just means baseline is untreated. SUDFA means no interference between a treatment unit and a comparison unit. No interference. Yeah, and you can't distinguish, right? Exactly. You cannot distinguish between Y0 and Y1. See, because the switching equation. See, you only observe Y. You don't ever observe Y0, Y1. You deduce whether Y is Y0 or Y1 based on the treatment assignment, right? So if D equals 1, then this outcome that you're observing is Y1. And if D equals 0, you know that this outcome that you're observing is Y0. And so that's where it's like anticipation creates some confusion. Like anticipation means I know it's coming, but does that mean that I've been treated? Not, so not necessarily. But to be on the safe side, you might want to just roll it back, roll it back a little bit, right? So here is the outcome regression model. Here's the outcome regression model. Heckman et al., 1997, and I have been meaning to change this, so I'm gonna. Hold on. This is the same thing, but it's easier to visualize if I do this. Okay, just like distribute out that. All right, so the outcome regression model is a kind of diff and diff. All right, so it's like this right here is the post period. This is the pre-period, right? This is the treatment group, right? So you do an average of Y in the post period for the treatment group minus the average of Y for the treatment group in the pre-period, right? So that's just a standard diff and diff. That's like this right here is just the first difference for the treated group. Okay. Then what's this? What is this? This is first difference in imputed Y0 for the treatment group. These mu hats, they've got like awkward notation, but basically the mu hat, mu equals expectation y for a group. Okay, so it's like for a group, you know, mu is equal to y. Right? It's equal to y as a function of x and as a function of d. So you've got like, you know, you've got a value of y based on x, right? So how do you get it? So mu hat is technically a prediction of y0 in a world where the treatment had never happened. It's a prediction of y0 for the treatment group in a world where the treatment had never happened. Using the x's at baseline and a regression using only the control group, getting estimated coefficients on the x's, and then predict y0 with those coefficients on those x's for the treatment group. Okay? This kind of technique shows up a lot now. I don't know, you know, like I'm going to show you a quote in just a second from Hide Ikamura, but like this kind of approach in Diff and Diff of taking the control group, fitting a relationship, and then using that fitted relationship to predict the missing counterfactuals for the treatment group, it's something that that the new imputation, this is something that all the new imputation Diff and Diff estimators are doing. Okay. And that's what Heckman's doing. Right. So what you're going to do is you're going to calculate delta y, right? Just the change in y over time for the untreated groups. Right. So you're going to literally run this regression. Delta y is change in y from pre to post for the control group. Okay. Regress delta y onto x's at baseline for d equal only. Right? So only do it for the control group. Why? Because the control group outcomes in pre and post are y0. Right? And that's what's missing. You're missing y0, and you're missing y0 in the treatment group. So you're going to use the evolution of y0 in the control group to impute the evolution of y0 in the treatment group, right? That's standard parallel trends, but it's based on covariates. So they had to build a parallel, build a machine that would do the prediction off the covariate values. And that's their outcome regression model. And it produces for each treated unit, mu hat x, which are as predicted y0 based on x. Predicted y0 for the treated based on the control group outcome regression model. That's the idea. I mean, that is what you're doing. So you're going to get those fitted values of the regression using all the covariates. Yeah, regress it, get the fitted values. Exactly, Waldo, we do. We do. That's right. It's going to have the same problem. It's going to have the same problem. So that's why what we said here is, this is going to require the correct model. Abity's going to require the correct model. Doubly robust is going to do both of them at the same time and only require that one of the models be right. Okay, so that's what you're doing with so it's basically yes, exactly. Exactly. It is based, that's great, Anna. It is imputation. Imputation with using the Y zeros. The only people that have a Y zero in the pre and the post is a control group, right? And under conditional parallel trends, this is the thing, under conditional parallel trends, the relationship between delta Y0 and X is the same for the treatment group as it is for the control group. So if you estimate the outcome regression model on the control group, okay? If you estimate it on the control group and you find fitted coefficients on the X's for the control group, conditional parallel trends means those fitted coefficients also are true for the treatment group. It's a correct deduction from conditional parallel trends. Well, because Trevor, you're calculating delta Y. So, your regression model is delta Y0. And there is no delta Y0 for the treatment group because you have Y1 in the post. So you can't use it. Because it's not, so it's like, it's not you're missing, you can't calculate the delta Y0 for the treatment group. So, you can't even, so you can't, there's no measurement for the treatment group. I think if you do not have confidence in I guess if you do not feel that you should use the outcome regression model, you shouldn't use it. In general, I'm not positive though. I'm not positive that's the reason not to do it. The unusual distribution, but you might see the unusual distribution part's not really a problem because the ATT is an average. So, you're just estimating conditional expectations with the regression. So I don't know. I need to think about that, Amy. For the treated units. You need overlap for the treated units. Yes. You need it to be that there are in the control group units with the same values of X as in the treatment group. You do not need the treatment group to have the X's of the control group. So you can have like a ton of people in the control group with really low propensity scores. And you don't need to find people in the treatment group with those really low propensity scores, but you do need to find people in the control group with the same distribution of the propensity scores in the treatment group. So it's like they're not, you don't, because you're not estimating the average treatment effect. You're estimating the average treatment on the treated. So since you're estimating the average treated on the treated, you really need the things to line up for who's going to be a good match for my treatment group. Yep. Okay. Sorry. We got Abity. Outcome regression model to Waldo's point. Outcome regression model still needs to be correctly specified. inverse probability weight still must be correctly specified. And you can't rank them. You can't rank them. You can't say like, well, one is always better in practice because they're both bad with respect to their own model misspecification. So there's no like theoretical ranking that you can say, well, outcome regression is always better. You know, its bias is always lower. You can't do that. So let's look at the 2A fixed effects. I'm going to get back to this, but what we're going to do is we're going to look at the 2A fixed effects and we're going to see. So we said here, we only need, panel or repeated cross-section data, conditional parallel trends, no anticipation, SUTVA, common support. All right. So with those options, we can use these two. And then we discussed them. What about 2A fixed effects? Why can't I just use a regression? Put in controls, right? So let's look at that. So let's look at our 2A fixed effects specification. This is one without controls. This is one with controls, right? So the question is, since I know, right, I know that this equals ATT plus parallel trends bias, right? Like that's what I know. So then does that also, if I just put in covariates, does this coefficient here also just go ATT plus parallel trends? You know, like is that going to be enough? And the answer is no. So you have to, there's this model has additional assumptions in order for this under parallel trends, in order for this to identify the average treated on the treated, you need more assumptions. So to show it, I'm going to kind of do the stuff that we've been doing where we like do all the substitution. I've got a horribly dry mouth. So 2A fixed effects, the thing it does is it's always placing restrictions on the data generating process. So what we're going to do is we're going to write down expectation Y1 for the treatment group, right? So if you're Y1 in the post period and you're the treatment group, conditional on X, then this equation right here, so it's like, this becomes alpha 1. So it's expectation Y1 if you're treated in the post. So that would be a 1 because it's post period. Your treated group, that's a 1, and it's 1 times 1, right? So then if you want to know what the 2-way fixed effects estimated average Y1 is, okay, then it's just the sum of all those coefficients plus this. There it is right there, okay? Now with conditional parallel trends, we can, if we assume conditional parallel trends, then we can write down what expectation, because we're going to get to an ATT, we're going to write down expectation Y0 in the post for the treated based on X. You could literally go through and calculate all this, but I find it just as easier to say this. So if it's Y0, if you add in fixed effects, you add in the fixed effects, does the assumptions that I'm about to go through change? Because the assumptions for including fixed effects, they're not really like it. Usually what you're doing when you're putting in the fixed effects is you're assuming that the outcome is linear in this unobserved heterogeneity. And then the fixed effects just deletes the heterogeneity by including those panel fixed effects. So it's more of a procedure. I'm not positive that for now, let's let's just look at the covariates. I want to say I need to get some advice to answer that question, Renz. Because if you think of the fixed effects as just part of the covariate matrix, then, you know, this theta will just apply to the dummies, the coefficient on the dummies. But I'm not positive that's right. So I need to think about that. All right, but look, we're basically writing down the definition of the average treatment on the treated. Expectation Y1 for the treated minus expectation Y0 for the treated in the post period. Kyle might know. So if it's the Y0, then there is no treatment, but it's the post period, you're the treatment group, and you got the X's. So it's going to be like this. So Y0 is going to be alpha 1, alpha 2, alpha 3, theta X. And Y1 is going to be alpha 1, alpha 2, alpha 3, delta theta X. Okay. So what we've done is we just have used the two-way fixed effects model to just get prediction, like, you know, use that model as a, you know, an equation that determines the Y1 and Y0s. Okay. For Y1 and Y0s. And when we did this before with diff and diff, okay, when we did this before with OLS and there were no covariates, we basically write this down and we like say this minus this, and so like that cancels out, and you're left with just delta. But see, watch what happens now. When we write down expectation Y1 minus expectation Y0, that's going to cancel out. That's going to cancel out, but we're going to end up with this. Okay. It's a little bit hard, I think, to really understand what I'm about to do. So I don't have this code written up as a diff and diff. I have it written up as a regression, but I want to show you what it means for the X's to have different coefficients on Y0 versus Y1. All right, because this is the part that confuses a lot of people. All right, so when we calculate the ATT and we say basically expectation Y1 minus expectation Y0, and expectation Y1 is this, and expectation Y0 is this, well, all the alphas go away. We end up with delta plus theta X minus theta X. But notice I just kind of added in theta 1, theta 2. And what does that mean? That means that, you know, I should put theta 1 right there. So if you think that the impact of X on the outcome depends on whether the unit has been treated or not, then those coefficients won't be the same. All right. So let me just show you with this other example, which I think you'll find interesting anyway. It's in a different folder, but it's not that one. It's not this one. I'm sorry. It's not this one either, but let me just check. Where is it? That's not it. Here it is. All right. So, yeah, this is it. So here I've got like a simulation. All right. I've got a simulation and I'm going to have two covariates, age and grade point average from high school. They're going to have different distributions. So I don't have common support. You can see here, they'll have different distributions when I try to visualize the imbalance. Okay. So there's like, I got a bunch of people in the control group with really high values compared to the treatment group. All right, watch what I'm going to do. I'm going to recenter, first of all, the covariates. All right, I'm going to create some interactions, and then I'm going to do this. All right, so look, Y0 is based on a constant in age, right? It's based on 15,000. Every unit in the data has a Y0 that's the sum of an intercept and a coefficient of 10.25 on their age, negative 10.5 on their age squared, 1,000 on GPA, negative 10.5 on GPA squared, and 500 interaction. Okay. So that's like saying that there's an X that determines Y0, right? Y1 is based on those covariates too, because Y1 is equal to Y0, right? So that means Y1 here is also based on X, but notice that the X's have their own effects on Y1. See how age has its own unique effect on Y1 and GPA has its own unique effect on Y1. And so here you see that whereas Y0, for every age you are, your Y0 only goes up by 10.25. With Y1, it's going to go up by, 110.25 because it'll be like this plus this averaged out. It'll be 110.25, which means that the coefficient on X is different depending on if you're treated or not. This is what what this is when you do this, all right, what happens when you have an equation like this, all right? What happens when you have an equation like this where the covariates are affecting each potential outcome in different ways? It creates heterogeneity in the treatment effects with respect to the covariates, and that'll cause your treatment effects to vary depending on your covariates. So we have here the average treatment effects of 2,500. For the average treat on the treated is 1962. The average treat on the untreated 3,000. Right. So if I had gotten rid of that and ran it again, then everybody's treatment effect is exactly the same. The averages you won't end up with heterogeneous treatment effects. So 2A fixed effects will be biased if the effect of the X's on Y1 is, and that's this one. If the effect of the X's on Y1 is different from the effect of the X's on Y0. Now see, right now this would be an example of it violating, and that would be an example of it not violating, because in that case, it would be, what's the relationship between X and Y0? 10.25. What's the relationship between X and Y1? Well, Y1 is equal to Y0. So it would still be 10.25. So in that sense, if the potential outcomes do not have if each potential outcome does not have its own, separate relationship with the X's, then 2A fixed effects will kind of ignore that there is no heterogeneity. So it doesn't really matter. But if there is heterogeneity, then 2A fixed effects will be biased. And it will be biased by the gap between these two relationships, right? This is called, when we assume this right here, we're assuming that the treatment effects are the same for all types of people defined by the covariates. So it would mean like the treatment effect is exactly the same, like here. Okay, so watch. Let's see. Some summarize age. All right, so it goes, let's see. So we'll go, some delta if age is less than 0. Right? So for those that are, on the lower half, the average treatment effect is 2031, some delta if age greater than 0. Right? For the older people, the treatment effects are larger. Some delta if age less than 0, 2,500. Some delta if age greater than 0, 2,500. All right. So you see here that what we've got is homogeneous treatment effects. The treatment effects are the same. 2A fixed effects will require that the treatment effects be identical for everybody. It'll require homogeneous treatment effects with respect to the X's. So if like X is sex. So Alexander was asking about exploring heterogeneous treatment effects with respect to covariates in a triple diff, which by the way, Alexander, I'll tell you what Andrew Goodman-Bacon told me, which is what I was thinking. And so if you believe that there's heterogeneous treatment effects with respect to the covariates, then this model right here won't even get that right. Put aside exploring the heterogeneity. Just simply there being heterogeneity will make that biased. So that's one thing. And then here, we're going to write down the diff and diff. And I need to, I was meaning to do this. I think that what would be good is if I was to, well, we'll just do it like this. So here you've got the conditional expectations from the 2A fixed effects equation, Y1 post, right, in the treatment period is equal to the sum of all those. Since the X's are changing values, then, these X's will be different. Okay, they'll be different for each of these in the pre and the post. All right, so you got post period D equal 1. It's going to be all those. Pre period D equal 1. It's not going to be alpha 2. Because alpha 2 is it the post period? Yes or no? If it's the post period, it's a 1. If it's the pre period, it's if it's the pre period, then it's a 0. Me telling? Yeah, no, I don't think that's, I don't think homogeneous. I think we typically believe that the treatment effects probably do vary by the people, by groups, and probably do vary by covariates. I mean, we have like entire models that are devoted to exploring heterogeneity with respect to the covariates. And Alexander's question yesterday was all about heterogeneity with respect to the covariates. So, you're already kind of like in a world where we sort of expect that the treatment effects probably do vary for blacks versus whites, for men versus women, for rich people versus poor people, for old people versus young people. We think the treatment effects might be different, So, okay, so we take these expectations, right? We calculate them all according to that 2A fixed effects model. And then we're going to put them into diff and diff. We're going to put them into diff and diff. And what we're going to get is that diff and diff is going to equal, these differences, right? So let's do this. So we'll alpha 1, alpha 3. Okay. All right, now I'm going to do alpha 1 minus alpha 1. That's going to cancel out. And so then I've got this term up here, alpha 2 minus alpha 2. And then I'm just left with the diff and diff equation when estimated with 2A fixed effects is equal to delta plus this right here. Okay. And so what is that? That is the trends in the X's. It's the trends in the X's from the pre and post period. And so if there are trends in the X's and they do not equal 0, these trends, if you have X specific trends, then this two-way fixed effects will also be biased, right? And this has to do with the time varying X's, whereas this had to do with homogeneous treatment effects. So you need no X specific trends for the treatment group and the comparison group. So no X specific trends means the evolution of the potential outcome is the same regardless of the covariates. So it would mean you cannot allow rich people to be on a different trend than poor people. So let's review the problem. You claim you need X for conditional parallel trends. You have 3 options. You can do outcome regression. You can use inverse probability weighting. You can use two-way fixed effects. Two-way fixed effects is going to need 3 additional assumptions. Homogeneous treatment effects with respect to the covariates and no X-specific trends. Problems, these 2 do not require, they don't require anything about homogeneity. So treatment effects can be heterogeneous with respect to the covariates. That's fine. And the time varying covariate stuff doesn't matter. X specific trends don't matter because you're not using covariates in the post period. You're only using covariates in the baseline. So what doubly robust is going to do is it's going to estimate both of these at the same time. You just need one of the models to be right. Two-way fixed effects needs homogeneity assumptions. Okay. So here's the doubly robust. Doubly robust is, I'm going to put up here, this right here, so you can see. So let's say you're the treatment group. Okay, you're the treatment group. What is my calculation going to be for you? Right? So if I am the treatment group, then I'm going to have delta Y right here, delta Y. And all of this is going to go away because that's a 1 minus 1. So then all of that goes away. So the only thing you're going to get if you're in the treatment group is you're going to get delta Y, right? Before and after, minus delta predicted Y0, right? That's what you're doing. So the only thing, so what happens first is that you've kind of got like this, like data set, okay? All right, so you have this data set. Then you have like person 1, 2, 3, 4, 5, 6, 7, right? And then there's like, you know, delta Y, and then there's like treatment, right? And there's going to be like delta mu hat, right? So then this one right here, maybe delta Y is like a 15. It's a treatment group unit. And maybe it's delta mu hat is going to be a 3. Right? Like that. So because what it did is it used the change in Y0 for the control group to basically impute what the change in Y0 would have been for the treatment group. Okay? So you're gonna always subtract. So you'd go 15 minus 3. No weights. No weights though. You're 12. All right, let's say then that it's like this is a 10. It's a 1. Say it's a 7. Then 10 minus 7 is a 3. So instead of having that be like, you know, what you're basically doing is you're basically adjusting the change in Y0 for the treatment group with this like predicted mu hat. Okay. What if you're the control group? Well, if you're the control group, that's a 0 divided by expectation E. So we're going to get rid of that. Right? I can get rid of this to 1 minus 0 is a 1. Okay. And then it ignores this. Okay. It ignores this. And so what you get now all right, so like for the treatment group, there's this estimated propensity score, but for the treatment group, it ignores it. The treatment group ignores it because it's not going to do anything. We predict mu hat with the outcome regression model. We predict mu hat. It's already double robust will do it. It'll estimate the propensity score. It'll also estimate mu hat. And mu hat is just so predicted mu hat is the same thing as predicted Y0. You predict Y0 by regressing delta Y0 onto X, onto baseline X for the control group only, and then use those fitted coefficient values and impute delta Y0 for the treatment group. All right. All right, let's say it's a control group unit. Then the control group unit will be like, let's say it's delta Y is a 5. It's in the control group. Let's say that its propensity score is, 0.7. It doesn't calculate a mu hat. It doesn't calculate a mu hat. It's just going to calculate a weight on the control group. So here's what it'll be. It'll be like, it's going to be P of X over 1 minus P of X, right? So it'll be 0.7 over 0.3, 2.3. So this will be 5 times 2.3, right? And so this final column right here will be averaged in doubly robust. Treatment group units will be adjusted by their mu hats. Control group units will not. Control group units will be weighted by their propensity score. Does both of them. All right. And that'll be doubly robust. We'll get this entire column of unit level delta Ys that are either reweighted if they're the control group or adjusted if they're the treatment group. Okay. And then we'll average over all this, and that'll be an estimate of the ATT. That'll be an estimate of the ATT. So authors exploit all the restrictions implied by the assumptions. They get these things called semi-parametric bounds. One of the main results is that doubly robust diff and diff. It's also doubly robust for inference. All right, so what we're going to do is we're going to take a real quick break, 15 minutes, and then we're going to look at this Monte Carlo simulation. And with this Monte Carlo simulation, we will see how two-way fixed effects performs against doubly robust, outcome regression, and propensity scores. Right? We're going to do all 4 of them in a simulation, 10,000 simulations, always the same sample size. And we're going to see how all of these perform against each other so we can sort of see with our own eyes how important these assumptions are. All right, so let's take a 15-minute break. We'll come right back. All right, let me look at this here. In terms page. Same group of Y1. We're looking at the same group of people. Well, they don't have to, Wen-Chin. That's an assumption. So, you know, I don't have like a diff and diff example here. I just have like a simple regression model. But the point we're trying to make right here is that the Y1s and the Y0s are for the same groups of people. The Y1s and the Y0s are for the same. The Y1, when I generate this right here, okay, and each of the observations, right, each person has their own potential outcomes. They have their own treatment effect. Okay. So you could have a person's potential, like think of it like this, Wen-Chin, like let's say the treatment is getting a PhD. Okay. The treatment is get a PhD. And the covariate is age. Okay. And age has some effect on your earnings, and your PhD has some effect on your earnings, right? Let's say the PhD's average effect is $10,000. So that on average, the PhD will increase your earnings $10,000. So then what is this like age part? Okay. Well, it's possible that people with a PhD have returns to their age that are different than those without a PhD. Okay. So basically what this is saying right here is that could be that the treatment effects are different for people with different ages. All right. And the way that you model that is that age has its own effect on Y1 that's separate from Y0. Okay. And so when you have that, when you have the case that the treatment effects vary with the covariates, then two-way fixed effects will be biased. That two-way fixed effect specification will be biased. That's the idea. Okay. And so all that you're saying is that, you know, if the treatment effects vary with the covariates, well, two-way fixed effects requires that they don't in order for it to be unbiased. But the others do not require that. Okay. Alexander, I'm going to follow up with you. But basically what Andrew said, what Bacon said was, Bacon said that what I was saying is correct. You can do something called regression adjustment. Where did he go? Okay, so here's what he said. So I said, let's say you have one covariate, sex 0, 1, you have a 2x2 OLS. You fully I said, could you, if you wanted to get different treatment effects, if you wanted to explore the heterogeneity with respect to the covariates, would you use regression adjustment? So this is not triple diff. I was just trying to understand the diff and diff. And I said, would you fully interact the dummies, the post dummy, treatment dummy? Would you fully interact them with the covariate? I know that's how you, so I said, how do you get from that? How do you get the conditional ATT, right? So if you just want to know the ATT for just women versus men, he said, interact the time fixed effect and the treatment times post with a female dummy, report the baseline, treat post coefficient. I'll have to write this out for you. Alexander, I'll write this out for you. I'll get like a better, more thorough thing. It's a version of regression adjustment. So I'll get it. It's a version of regression adjustment. So, that's what it is. All right, so let's look at this example. We're going to do yeah, I know. I'm a little winded a little bit. So here we have the 10,000 Monte Carlos. Okay. Every data set will be 1,000 observations, and we're going to estimate treatment effects, which are going to be determined by this Monte Carlo using double robust, two-way fixed effects, outcome regression, inverse probability weighting. Yeah, here's a Monte Carlo. This is a Monte Carlo. It's running through this. Oh gosh. Hold on. Monte Carlo will run through and create the data it's a simulation. All right. So what it's going to do is it's going to create a data set, a treatment group, some covariates, generate the raw data, generate the treatment effects. All right. And then it's going to be a different data set each time because of some random noise. So there'll be random noise coming from the covariates. The covariates will be on average this, but they'll come from this distribution. And then the potential outcomes will also have some randomness. It'll run through it all these times. Okay. So that's what my simulation here is doing for a different data set, for a different thing. Okay. So it's going to do 10,000 experiments. Mine right now is doing 1,000, right? It's doing 1,000. And each time that it runs, it's a slightly different data set because of the randomness of the covariates and the randomness of the potential outcomes. Even though there's parts of the potential outcomes that are not random, which are these coefficients, the variables will be slightly random, and then there'll be an error term. All right. So you'll run through it 1,000, you run through this 1,000 times. Each time in this, you'll run a model. So here I'm running matching. I do a regression adjustment model. I do another regression adjustment model, and then I do regressions. Okay, regressions. That is what he's doing. He's doing sample size 1,000. My sample size is 5,000. He's doing 10,000 Monte Carlos. I'm doing 1,000. He's estimating 4 models: doubly robust, two-way fixed effects, outcome regression, IPW. In my simulation, I'm doing 10 models or 11 models or something like that. And then his propensity score, now we're just sticking with what he's doing. His propensity score is going to be estimated every time with Logit, and his outcome regression is going to be estimated using the linear specification. All that means is that like he's got like here, it would be like this model, like the inverse probability weighting model. There'll be some command that says use logit. And then this outcome regression model, there'll be some, like it might be this one, have a command that says use OLS. Okay. That's it. 10,000 simulations, you get a distribution. Okay. You get a distribution, you can get a standard error, which is to be the standard deviation in those 10,000 coefficient estimates. Okay. So, and then you can also get the fit of how good the fit is, the root mean squared error. And also you can get information about the confidence intervals. I'm just going to focus, I think, on this and this. All right. So if you have in this data that he generated, right? So Pedro generated a data set, 10,000 data sets. Okay. With randomized covariates, slightly, some random covariates, but with fixed, parameters on them. 10,000 data sets, randomized covariates, etc. And then he estimates 4 models. Number 1, 2A fixed effects. And it's going to be something like this. Y equal, Y regressed onto, it'll be Y regressed onto post-treatment, post times treatment, and then covariates. Okay. And then he'll report coefficient on post treatment, because that'll be the diff and diff coefficient. Number 2, he'll do IPW, estimate propensity score, weight the comparison group by IPW. 3, he'll do outcome regression, estimate delta Y0 for treatment using control group only and baseline X. And then 4, doubly robust, do both. Okay. And in the data sets that he makes, his data generating process, okay, his data generating process for the potential outcomes will be no anticipation, SUTVA, conditional parallel trends, common support, but he won't assume homogeneous treatment effects with respect to the covariates. So he'll have treatment effects that vary a lot by the covariates, and he'll have he won't assume no X specific trends. So he will have trends in the covariates over time for both groups. Okay, that are different trends in the covariates. So this 2A fixed effects cannot handle, and the other 3, they all need conditional parallel trends, no anticipation, SUTVA. 2A fixed effects does not need common support, but it does need these other 3, right? So we're going to see, well, how well do these 4 models do on average if you can satisfy these 4 things in the data generating process, but you don't have that. So it's like, what he's basically done is when he's assuming heterogeneous treatment effects, it's like what he's going to have is something like this. He's going to have treatment effects that differ by the covariates. 2A fixed effects can't handle that. He's going to have X specific trends when he's generating the covariates over time. There'll be trends. I should make this a simulation myself, but I haven't done it yet. It's on my to-do list. All right. So here's what you get. 2A fixed effects. It is biased. Why? Because He does not have homogeneous treatment effects with respect to the covariates. He does not have X specific, he has X specific trends. So it's biased. The other three are not biased. This is all they need. And so they're unbiased. On average, there is no bias. All right. But the variance of the inverse probability weighting is kind of large in the way that he generated the data. So he generated the data such that inverse probability weighting is going to end up having this lots of variation in the estimate. You would check it. You would check it with the event study. That's the only thing you could do, Sinchita, is just use, you're always checking conditional parallel trends with event studies and falsifications. It's all you can ever do because it's not testable. So you can see here, look, so outcome regression, unbiased, and has a very good fit, and its standard error is really small. So the standard deviation across these 10,000 simulations is 0.1, right? Inverse probability weighting, also on average, has no bias. The fit is not as good. It's still better than two-way fixed effects, but the fit is not good. And its standard error is 2.6. So, you know, it's on average 0, but it's got a large variance of the IPW sample, the sample variance, this variance of the estimator across 10,000 samples. The standard deviation of it's 2.6, which the number doesn't mean anything. It just means, notice though, it's like much higher than this one. Now look at doubly robust. Even though doubly robust does inverse probability weighting and outcome regression, okay, it's more like outcome regression than it is IPW. And even though it did IPW, it's not got the large standard error of IPW, even though it did it. Even though it did it. It looks more like outcome regression. So let me show you. Here is OR. This is Heckman's thing, doubly robust. And then this is the inverse probability weighting. There's these two things that he does. Doesn't matter. It can be calculated because it's a simulation. See, like right here. All right. So like I know, okay, because I generated the data, I know that the average treatment effect is a 2,500. All right. And if I'm looking at the treatment group, I know that the average treatment effect is 1962. So if I run a regression and I don't get, 2,500, it's biased. So I run this regression, I don't get a 2,500. So it's biased. Okay. So he's saying, like, on average, it would be like this. I do this 10,000 times. On average, it's a 2,500. So on average, it's unbiased. So that's what this means. So every now and then, it's a little bit biased. Okay, so it's like a little bit biased. Outcome regression sometimes is biased. Sometimes it's biased this way. Sometimes it's biased that way. On average, it's 0. Yeah, it's fake data. It's fake data. Thank you. So then on average, it's 0. The variance is, is this full spread. You can calculate the variance, and the standard deviation would be like right there. Okay. So that'd be the standard deviation, which is about a 0.1, which is why that says 0.1. Okay. That's outcome regression. All right. Doubly robust is nearly identical. It's nearly identical to the outcome regression. Now, this one is actually the worst of them all. It looks like it's tighter. It's not. Notice the x-axis is going 0.25. This is going 0.3. Standard deviation in this is like, 1 point, I don't know. It's like, says it's 2.6. So, what does that mean? That means when I do this, depending on the sample of data I get, that I happen to randomly get, I might be anywhere from a bias of -3 to 3. It's like it runs all the way from 6 to -6. Like I could be anywhere in there, but most of the time, the average is going to be unbiased. Okay. So the larger the variance is, the more worrisome it is because, you don't know which of those 10,000 data sets you pulled. You know that the estimator is on average 0, but you don't know which one you pulled. Exactly. Young Swan brings up a really good point. So this is so to Young Swan's point, everything that we are saying right now is about this regression model. Two-way fixed effects with additive covariates. It's the same thing I was doing over here. Okay. I ran a model with additive covariates, regress an outcome onto covariates, added in separately. Okay. But there's a method you can use called regression adjustment. And what regression adjustment does is it fully interacts the treatment with all the covariates, and then it has to like pull them up and then do this ridiculous thing to get the ATT. And it's called regression adjustment. So Song says, Young One Song says, people suggest including interaction terms between pre-treatment covariates and post-dummy and two-way fixed effects, instead of including the time-varying covariates. Thus, this is to control for covariate-specific time trend. I wonder if this method is better, to what extent the simulation results change. It is better. It is better. The two-way fixed, two-way fixed effects is not really the problem. This is the problem. This model of running the model with time-varying controls and just allowing them to just be in there additively is the reason. It's the reason that this is so biased. I do this simulation here, and I know that the treatment effect is 2,500 right here. And I know the ATT is 1962. If I put in just the covariates without any interactions, I don't get the right number. But if I want to get the ATT, right, I do exactly what Young Swan said. I say, I interact the treatment with all the covariates. And Alexander, this is kind of what I was trying to read off with what Andrew was saying. I interact treatment with all the covariates. I get coefficients when I do this. Here, when I do that, I get all these coefficients on the interactions, right? So I get coefficients on the interactions. And then it's just a matter of, if you want to get a specific causal effect, you have to just use these coefficients in certain ways. So like if you want the average treatment effect, there it is, 2,500 on the dummy. But if you want the ATT, you have to basically take each of these interactions, sum them together, multiplied by parts of the data, and then you'll get this. Now, if you remember, sum delta if treat is equal to 1962. When I did this full crazy thing, I got 1962. So that's called regression adjustment. Regression adjustment is what Young Swan said in the Zoom chat, where you interact the pre-treatment covariates with the post-dummy in the two-way fixed effects. You do this fully saturated model. And what I was going to write down for you, Alexander, is like, so how do you take each of these coefficients and then reproduce like the effect just for men and the effect just for women? And you do the same thing. You do the same thing, but like it's a different adjustment. Okay. So that's a very good point. But the reason why Young Swan's exactly right. There is a way to make two-way fixed effects better. it's a fully saturated regression adjustment model, which is basically what Wooldridge's Moonblock estimator does. But we're just trying to criticize right now standard practices, because standard practices are just run a diff and diff, put in the controls. Is that enough? And the answer is no. Because if you have heterogeneous treatment effects, it won't work. And if you have X specific trends, it won't work. Okay. These don't need heterogeneous treatment effects. These don't need homogeneous treatment effects, so they're not bothered by it. And these don't need anything about X specific trends because they don't use post-treatment X's. But the point here is that doubly robust still has these nice properties, is because even though both of the models were correctly specified, right? Both models were correctly specified. The propensity score, I'll get a better answer, Alexander, and I'll put it in Discord. So we see here doubly robust is not really getting pulled in the it's not doing as bad. But what if you misspecified the outcome regression model and you misspecified the propensity score? What would it do then? So he reruns it. He runs it 10,000 times, a different data generating process. This time it's a different one. So it's like doing this all over again. Okay. It's like doing this thing all over again, but with a different data generating process. And he's going to have the outcome regression model be wrong and the propensity score model be wrong. Okay. But still has all those heterogeneities. Well, two-way fixed effect is still biased. It's negative 16. Why? Because he didn't do what Young Swan said. He does not estimate the saturated model. He's just estimating the old-fashioned, put in controls. Okay. And just putting in the controls with this heterogeneity is not enough. So you have to use a different regression model for that. But outcome regression, it is biased. Here we now have a bias of the outcome regression model. Inverse probability weighting, lower. Doubly robust isn't as bad as outcome regression, not as good as propensity scores. They're biased, right? So here's the outcome regression. Its bias is like right here. Like it's on average equal to that. Okay, so that's what it is on average. It's probably like a -6, -5. So it's off by like 5. Is that right? Yeah, it's off by 5. Okay. And inverse probability weighting is equal to a -4. And that seems like it should be, well, maybe that's not, maybe it's more like that. I don't really know why that doesn't look exactly like I was thinking, but it said IPW is only going to be a -1. Looks like it's something else. I don't know. I don't have the raw data. So, but notice doubly robust is doing both of these at the same time, but not as bad as the worst one and not as good as the best one, but still better than the two-way fixed effects model under that data generating process. It all kind of really does depend on how big the heterogeneity is. If you really do not have much heterogeneity in the treatment effects with respect to the covariates, then, when you look back at the bias of two-way fixed effects, if those are approximately equal to one another, it's not going to be a big deal. If you don't have a lot of heterogeneity, it won't be a big deal. And if you don't have these X specific trends, that also won't be a big deal, right? So, but that X specific trends is again about heterogeneity. So the point here is that what really is killing two-way fixed effects is that this two-way fixed effects model right here This two-way fixed effects model assumes constant treatment effects with respect to the X's. And it assumes no X specific trends. That's what it assumes. That's what it assumes. And if you do have that, well, the model basically assumes you don't. And if you do, it'll be biased. Okay. The way that you get around it and still run a regression is you're going to have to do a saturated model. Fully interact the treatment indicators with baseline covariates and all of the dummies. All of the dummies. And then you got to recover them using a formula like this, or there's a command in Stata that does regression adjustment that'll do it. So now there's canned packages that will do this kind of regression adjustment for you with Diff and Diff, but there was not. It's very hard. It's very easy to get it wrong if you do it yourself. If you do it yourself, you can get it wrong very easily, because if you're doing what Yang Swan said, which is just fully interact the baseline covariates, you're supposed to technically dummy out all the covariates. If you interact that with the post dummy and the year dummies and the state and all this stuff, and then you sum them together, if you make any mistakes, you'll not get the number right, even if the original model was right, because regression adjustment kind of has like two stages. You like interact, that's easy, but then you collect the terms. That's hard. So you want to there's new packages as these regression adjustment models have become more popular. There's packages that do this for you. You never want to do it yourself. Okay. So there's code R in Stata. All Diff and Diff estimators are now beautifully arranged at a website hosted by Asjad Naqvi. Here. Okay. And so it's in here. You go down here to DRDID, who's written by Fernando Riaz Avila, Pedro Santana, Asjad Naqvi. It's based on the paper that we looked at. And you also have it in R. Here. And that was written by Pedro and Bean Zhao. Okay. You use covariates if you use covariates to reestablish parallel trends. It has nothing to do with heterogeneous treatment effects. Conditional parallel trends just means that the Y zeros are not evolving the same. Y zeros. Parallel trends is always about the Y zeros. Treatment effects are about Y1 and Y0. Okay, so when you're making an assumption about parallel trends, you're only making an assumption about the evolution of the outcome for the treatment group and the control group had the treatment never happened. Is the evolution the same? And if you say no, but then you think, but I think it could be the same for groups that are similar, observationally similar, then you can put it in. And that'll reestablish parallel trends. I mean, if you're right, it'll reestablish parallel trends. The most ideal circumstance would be if you need conditional parallel trends. Anytime you need Diff and Diff, the ideal circumstances would be, I believe that I do not have parallel trends unless I only have parallel trends for the covariate for units with the same covariates. Then I have it. That's when you would want to use doubly robust. Why? Because it's a much more, it's an estimator that has fewer assumptions, does not impose any homogeneity on the treatment effects, does not require anything about the evolution of the X's, okay? Or you could do some regression adjustment method, which is what I keep saying, I keep saying Yongsung's name, Youngwon's name, but Youngwon basically alluded to a regression adjustment method for diff and diff. You could do that too. Anytime, though, point is, anytime that you believe that you need covariates in your diff and diff, you should be looking at doubly robust, inverse probability weighting, outcome regression, or a regression adjusted to a fixed effects, the fully saturated diff and diff. And, you know, it's not one that I've really ever seen anybody do. So we're sort of just criticizing the standard practices. So you can kind of see, Waldo, like Wenchen, now that you hear me say it, the ideal circumstances for this is if I have to control for covariates, well, then you probably are like, I should probably be doing it a lot more because many of us are running regressions with covariates. But there's been a lot of papers that have come out recently that have begun to really show that these OLS models like this OLS model right here, where you just add in covariates, is biased. It like this is an example. This one right here. This is just a normal data set. Like that, sorry, this is just a normal regression, cross-section regression with covariates. Okay. I generated this data here. I got imbalance in the covariates. The Y0s are based on the covariates. The Y1s are based on the covariates, but Y1 is based on, has a different coefficient on the covariate. So Y0, coefficient on age is a 10.25. For Y1, it's 10.25 plus 100. So it's 110.25. Okay. So I know right here that the average treatment effect is $2,500 because I programmed it to be that right there. When I go delta equals Y1 minus Y0, it'll go Y1, which is all this, minus Y0, which is all that. So then this goes away, and all I'm left with is this is what Y1 minus Y0 is. Yeah, good question, Becky. That's a great question. There's a way to do it. There's definitely a way to do it. I would probably have to sit down and I've never seen a package that does it. You would have to probably adapt some of these packages to do it. Like I do have, Becky, right here. Pedro gave me a triple difference version of his Callaway and Santana estimator. And it will do triple differences off of the I can't even get it to open. So it'll do triple differences manually, okay, using his Callaway Santana. He had to basically rewrite Callaway Santana just to do triple differences. And once you put in covariates, it changes. So I guess, Becky, my answer would be, I am not positive that we know a lot about the properties of triple differences with covariates, what all the assumptions have to be. Pedro's kind of been like texting me a little bit about it. And there's a bunch of weird embedded assumptions that he's not written it up, but it's it's a little more difficult. So probably I would do something like what Youngwon said, which is some sort of regression adjustment. But even then, there's no regression adjustment
that I've seen for triple differences. Is it safer to do without covariates? But see, Saban, if you say that you need parallel trends with the covariates, then no. It's just nobody's built that yet. Nobody's built it. So probably what you would have to do, Becky, is you would have to say, if you're doing triple differences and you had to put in covariates in order to establish parallel trends, you would just simply have to assume homogeneous treatment effects. You just have to say it. You have to say, I'm assuming homogeneous treatment effects. I'm assuming no X specific trends. You just have to say it, because that's unless you have an estimator that you could kind of build on this material that will accommodate this. That's all I can think of. I mean, I could probably sit down and think of what, like, roughly what the covariate adjusted triple diff would look like. I mean, I could probably figure it out, but because it's going to be an analog to these things, but I don't know it off the top of my head. But like, this has been like a really common thing that, you know, here I know that the treatment effect is 2,500 and I know that the ATT is 1962. I know it is. And I know the covariates, age squared, GPA, GPA squared, and an interaction. Okay. I run that regression. The treatment effect is 2,500. And the treatment effect for the treatment group is 1962. And that's not a 2,500. And 2,500 is not in the confidence interval. And it's definitely not 1962. So like, this weakness of two-way fixed effect specifications is getting more and more attention. This is a misspecified OLS model. The correctly specified OLS model is this one. Fully interact, treatment, all the covariates. Okay, so look at this, watch. We know that the effect of age is a 10.25. Watch what we get here. On age by itself, that would be the Y0 stuff, 10.25. On the interaction, 100. On age squared, it should be negative 10.5, and it is. But on the interaction, well, age squared doesn't determine Y1. So notice that's a 0. GPA on the Y0 part is 1,000. There it is. For the Y1 part, it should be 1,100. There it is. For GPA squared, for the control group, negative 10.5. There that is. For the interaction, well, it doesn't depend on GPA squared, so it should be a 0. There it is. The interaction, 500. Of age and GPA, and then interacting that with treatment, it should be a 0 because it doesn't depend on it, and it's 0. Okay, so here it kind of goes through, does the whole thing, takes all these coefficients, sums them, and then you have to multiply each of the coefficient by the mean of the covariates in the treatment. I mean, it's really crazy what you have to do in order to get this right. If I want to get the average treatment effect from this fully saturated model, I just look at that part. And if I want to get the average treated on the treated, I got to take that, and that, add them together, multiplying each of the coefficients by the average of these covariates in the treatment group. Sum them together. And then it'll get it right. So like, this is the truth. And then that's the regression adjustment, and it'll do it. So if you were going to do triple difference, all right, if you were going to do triple difference with covariates, it would be a version of this. regression adjustment. You would have to interact all the covariates with basically, I believe you would have to interact it with essentially every year effect, like I think you'd have to do it with the interact everything with the covariates and the treatment, and then do your own summing. It could easily be mistaken. I'd have to work that out, but that's basically what you'd have to do. Okay. All right. So let's take a 15-minute break. I'm going to answer these questions now. Take a 15-minute break. We'll go for 45 minutes. We'll go for 30 minutes. Take a break. And then Kyle will then do his discussion of the Moretti and Klein paper. So we'll be right back. I was just talking to Kyle, and what we're going to do is we're just going to I'm going to do a quick run through of some, this one particular replication that we've been working with, the Lalone data set. And then Kyle is just going to start at 3:45. And if we finish early, we finish early, because I know it's been a long day. And so we'll go ahead and do that. So my part will only go for like 30 minutes. All right, so we're going to look at a real example with real data, see how well this does. It's a famous paper in the history of causal inference, at least in economics. It's by Bob Lalonde, 1986 article. He was a student of Orley Ashenfelter and David Card at Princeton's. And basically, I'll explain what he did in a second, but it evaluated a lot of estimators, found that they all did really badly. Okay, we're going to see how badly it does, though, with diff and diff. So there was here was the study that was done in 1986. So it was a randomized control trial done by Manpower Demonstration Research Corporation. And the name of the program was the National Supported Work Demonstration. That's what's called NSW. And what NSW was a temporary employment program designed to help disadvantaged workers that lacked basic job skills get those job skills, move into labor markets by giving them work experience and basically kind of giving them some counseling, but doing it in an environment where if they messed up, they wouldn't get fired. So it's kind of what they were trying to do. It was like a lot of the people in the experiment a lot of them were women on very, very poor. It was very, very poor people, women that were receiving welfare payments from the American government, people that had histories of substance abuse problems, people that had been in prison or jail, or high school dropouts. So it was a very selected group of people. Okay, it was a very selected group of people. They randomly assigned the NSW program to a treatment group, and then the control group, they just were like, they were not in it. And then they followed up with them like every couple of years. Okay. Here's a little bit more about the program. Treatment group members, they were guaranteed a job for about a year and a half. And it depended on the target group, depended on the job site. Basically, then the treatment group was divided into crews, 3 to 5 participants. Okay. They all worked together, and then they met frequently after work with a counselor. And they would meet with the counselor to talk about their grievances at the job. This was the counseling part. And they would also just discuss their performance. And then they were paid. They were paid for their work. Okay. Control group members were randomized, so they were on average identical, right? The treatment group and the control group were on average identical, presumably on unobservables, but we could check their observables, right? Randomization should have balanced observables and unobservables across both arms. Therefore, if you just compare them to one another, you don't need covariates, you don't need parallel trends. You'll just compare them to one another, you get an average treatment effect. for people that look like this. Okay. People that look like this on covariates. Okay. Let's see. That's it. So I used to write this up so much. There's estimation. All right. So then what Bob Lalo, all right. So then the experiment was compare the average earnings for the treatment group with the average earnings of the control group in the randomized environment. Okay. And that'll give you the average treatment effect. Okay. In the original paper by Bob Lalone, 1986, the average treatment effect is $900. There's a follow-up paper that we're going to work with. Okay. There's a follow-up paper by Dejia and Waba. Dejia and Waba got the idea for this in a class taught at Harvard by Hito Embens and Don Rubin in the mid-90s. And so they decided to revisit what Bob Lalone did. To do it, though, they had to work with a select sample of the data. And in that select sample, they got to $1,800, right? So it's like a smaller sample, and the average treatment effect for them is 1,800, right? So what did Bob Lalone do? Bob Lalone was not studying the program. The program was done by MDRC, Manpower Demonstration Research Corporation, earlier. So a big book came out, and everybody knew that this was the effect, that it worked. I don't know whatever happened to that program, but they knew about it. Okay. Probably insights from it get incorporated into a lot of other stuff. Anyway, he was not trying to evaluate that. He was trying to evaluate econometrics. So here's what he wants to know. All right. Most of the time, people are not working with an RCT, right? If they're wanting to study a program, they're usually doing observational stuff like we're doing in this class. They'll be doing diff and diffs or whatever off of non-experimental data. So what he did was he said, well, I know the effect is $900, right? Because I got an RCT. I'm going to drop the control group. Just going to drop it. And I'm going to replace the control. So I'm going to leave the treatment group as is, but I'm going to drop the control group, and I'm going to replace the control group with survey data from two different surveys. Current population survey, which is a random sample of Americans. Panel study of income dynamics, which is a random sample of Americans. Right? He has like two nationally representative survey data sets. So this is going to be, the treatment group is going to be basically people like this, and the control group is going to look like the average American population in 1978, right? He is then going to compare the earnings of the people that were randomly assigned to the treatment, but now it doesn't have the right control group. Now it's got an observational control group, right? And so he's going to compare his randomized treated units, people that were self-selecting in, he's going to compare them to non-experimental control groups, people that are not random. And he's going to see if he's going to go through basically every single econometrics model that was like very sophisticated at the time. He's going to see if he ever gets a $900. And he doesn't. His estimates are way off. He knows that the answer is $900. He's working with the real treatment group units. He's just replaced them with control group units, and he has done all kinds of stuff. His estimates are way off. They usually have the wrong sign. And, so basically it's like, here's sort of the thing right here. Here's he's got a bunch of weird things he calls diff and diffs. They're not exactly different. I don't really understand these diff and diffs, but he's got diff and diffs in here. Yes. And everything down here is with the different data sets. So when he just compares the earnings of the people in the treatment group to the control group, the real answer is anywhere between $800, $900. Okay. When he just looks at, when he throws out the control group and replaces it with another group of non-experimental control group units, notice how many negative coefficients he finds. Okay. So he's not even getting the right sign, even when he starts trying to control for covariates. Adjusted means controlling for age squared, years of schooling, high school dropout, race. Then he does diff and diffs, unrestricted diff and diffs, controlling for, and it never really works. Okay. So the problem was one of the problems was the treatment group and the control group just looked radically different. All right. I think one of these things is wrong, but this is not correct. It's not that. So I don't think that number's right. But anyway, 297 treatment group units, 80% of them are Black. In the non-experimental control group, 7% are Black. On average, the treatment group is 24, but in this non-experimental data set, they're on average 33. 17% are married in the randomized treatment group, 71 of the CPS data, 73% never finish high school, 30% never finish high school. They'll have on average 10 years of education. The American population, they have on average 12. And here's the big one. Their wages in 1975, the year at baseline, that's baseline, was 3. I don't know. I can't remember what this is, 3.1. And that might be a log. And so or maybe it's 3,100. And then for the average American, it's 13. So it's much, much lower and much higher unemployment amongst the treatment group than the non-experimental control group. All right. So what we're going to do is we're going to go here. Causal inference 2, lab, Lalonde. We're going to answer questions 1, 2A, 2B, 2C. All right, so here we go. NSW data sets, one of the most commonly used data sets in econometrics, based on Lalonde and Deji and Waba. Both the original as well as the follow-up use the data to evaluate contemporary approaches to causal inference using non-experimental data. Cleverly, they start with an experimental data set to establish the true causal effect. Then they use a non-experimental data set consisting of a control group of randomly sampled American households to see if covariate adjustment can recover the true effects under fairly dramatic selection problems, right? So what we're going to do is this. We're going to perform analysis on the experimental data set. Here's the data set here. And we're just going to do a couple of things. One, under random assignment, simple difference in means identifies the ATE. And since the NSW was randomized, we can do it. So what we're going to do is we're going to calculate simple difference in means on the experimental data set, estimate the treatment effect, 2 separate ways. Manually calculate the averages, and then use them to get the returns, and then we're going to estimate OLS. All right? So let me show you. And this is available in R also. All right, so here we go. So you're going to need to install SSC install DRD. All right, so here we go. I'm going to load the data set in. Let's just look at it. All right, so it's 1,335 observations. Why? Because we're going to have 4 years of data. All right, we're going to have 4 years of data, 3 years of data. 1978 is the post-treatment. 75 is baseline. 74 is the year before baseline. Now, there's a little bit of something different here. All right. So in the original Lalone data set, there were 297 people in the treatment group. We've got 185. Why? Because we are going to use, where is it? We're going to use the subsample from Dajia and Waba. This is the Rahi, Dajia, Sadiq, Waba. They do it, and when they have to use a slightly smaller data set. It's all about covariates, and with their slightly smaller data set, they're going to find a treatment effect of that's a little bit bigger, 1794. Okay, so let's do that here. So we're going to do we're going to calculate those averages and just compare. So if you're treated and it's 1978, you made $6,349. And if you're in the control group, the randomized control group, you made $4,554. 6,349 minus 4,554 is 1,794. 1,794. There it is right there. Okay. So that's what that is. Then we're going to run a regression. Regress real earnings in 1978 onto a dummy if you were randomly assigned to the treatment group. 1794. 1794. Okay. So same thing. All that the regression does is the simple differences in means. Now we're going to do a diff and diff. Part B, estimate the effect of the treatment ever treated on real earnings using diff and diff. Okay. With the randomized experiment. Okay. We're going to have 78 be the post period, 75 be the pre-period. We're going to ignore this 1974 for now. We're going to do it two ways. Manually calculate the four means that you need for the diff and diff equation, then estimate it. Estimate the ATT using the OLS specification. Remember to only use 1978 and 1975 in this analysis. Right? So here's the difference in means. Now this, we're going to go through, we're going to go average real earnings if you're control group 75, average real earnings if you're control group 78, average real earnings if you're treatment group 75, average real earnings if you're treatment group 78. Then I got to create a single variable that has all of it. There's my diff and diff equation. And I find a 1529. It's not actually 1794 because this data set has a little bit of some weird properties to it, but it's 1529. Now I'm going to do a diff and diff. I'm going to generate a post dummy, interacting with a treatment dummy. I'm only going to be working with 75 and 78. 1529. 1529. Okay. So I found 1529. Then we're going to check for pre-trends. Now I only have one year before baseline. It's 1974. But I'm going to check for pre-trends anyway. Two ways. Manually calculate the diff and diff equation on 1974 relative to 1975. Estimate the dynamic OLS specification of ever treated with 74 and with 78, but omit 75. Here's the event study. I'm going to calculate 75 to 74, 74 to 75 using the diff and diff, and we're going to using the diff and diff equation off of the pre-trends. And so does the evolution of the treatment group's earnings going from 74 to 75 looks similar to the evolution of earnings for the control group going from 74 to 75. And the treatment group fell by $276. Okay. Out of like $1,300. So it's not trivial. It's not a great sign for parallel trends. But let's now do the OLS specification. So we're going to have a dummy for pre. If it's 1974, we're going to have a dummy for post if it's 1978. And we're going to interact ever treated with the post and the pre. We're going to see if we get negative 276 off of that coefficient and then the 1500 whatever off of the other. All right, so here we go. 1529. Okay, that was the diff and diff calculation we got just a minute ago. Negative 276. Negative 276. There it is. Okay. So all that did was just kind of show, you know, like how to do it. Now we're going to do the alone part. We're going to turn to the non-experimental data set. We're going to repeat 1A, 1B, 1C. We're going to repeat it. Well, actually, no. I'm not going to do the, I don't think I do. Anyway, I'm going to repeat it, but I'm going to use the non-experimental data set, right? So remember, the non-experimental data set has a very, very severe selection problem. Okay, so the earnings of the control group in the experimental data set was 4,554, but the earnings for the people in this CPS data, 14,000. So when you just compare the treatment group earnings, which was 6349, again, which with the randomized control group, you found that $1,800, but when you do it here, you can find a negative $8,500. Okay. Do the difference in means. Find the same thing. Negative 8497. There it is. Okay. There's that is right there. Now I'm going to do a diff and diff. Okay. I'm going to look at changes in real earnings from 75 to 78 for the treatment group, 75 to 78 for the control group, calculate diff and diff. So I know that the treatment effect is 1794. And I know when I did the diff and diff earlier, it was like 1500 and something. So let's see what it is here. When I use my non-experimental data set, let's see how diff and diff performs. Let's see if I get a 1794 or a 1500. I got a positive number, but it's way too big. It's like 3 times larger. It's not a great, you know, it's real, Amy, it's really not a very convincing case of pre-trends, probably. You know, you've got things that go all the way up to the size of the treatment effect. Well, not the size that that's the treatment effect, but you've got negative numbers. It's not really, this data set's kind of weird. And even though it's an RCT, this subsample, it's like a whole backstory, but the subsample has some issues. And I just really want to illustrate how to make the event study, like how to calculate it, let you understand that it is just a diff and diff equation on each of the coefficients, but I wouldn't say it's like the most convincing for parallel trends. So we have here the diff and diff estimate of the ATT is $3,600. Well, that's not right. That's not right because we did it earlier and it was like $1,500. So now I'm going to do diff and diff with an OLS specification. That'll give me a standard error, 3621. Significant, but doesn't even contain the truth. Okay. Then we'll do our event study pre-trends using, let's see what the pre-trend looks like. $197. That's closer to zero. We'll do the OLS model, $197. There's our estimated ATT. Something's definitely going on for sure. Treatment group is definitely going up a lot, but it does not cause them to get a $3,600 increase in their earnings. That's not true. So here we're going to run a regression. Okay, we're going to run a regression of real earnings onto an ever-treated dummy, post-dummy, with all the controls. Let's see what happens. Now, I don't have any person fixed effects in there, so these covariates are not going to get killed, but I'm going to see what the coefficient is on that. Didn't work. Now I'm going to do doubly robust. Doubly robust command, you have to install it up here. Doubly robust, real earnings, put your covariates in. Tell it what the baseline is. I'm going to say if it's 75 or if it's 78, get rid of the 74, comma, say what your time dimension is, say what your indicator variable is, ID, say what your treatment variable is, ever treated, and then report all. What does that mean? It's going to report outcome regression, Abbott's inverse probability weighting, and then doubly robust, and then some variations on both of them. Now remember, the truth is 1529. Okay. All right. So we've got doubly robust inverse probability weighting, doubly robust improved estimator, outcome regression model. Here's the IPW that we discussed, something called standardized IPW estimator, and then IPW and regression adjustment estimator. Okay. So outcome regression will be reg. IPW will be Abbott. Remember, the truth is 1500 and something, 1769. When we did just control for covariates, 3500. When we do these others, we're getting pretty close to the 1500. You know, outcome regression, 1769. Inverse probability weighting, 1860. Doubly robust, 1979, 2032. And then these standardized IPWs, a little bit better. You know, so this is the estimate of the average treat on the treated. Well, you would probably want to use the, let me see. Here we go. So either one of these, they have a slightly different propensity score. So the DRIMP is the improved doubly robust diff and diff estimator based on IPW of a tilting. And I have not studied the tilting papers. So you can do either one of them. This is this stabilized IPW weighting, which uses a particular change in how the propensity score is calculated. Oh, it does, 2032. Yeah, so it got written first. And then when the Stata one was written up, they added a bunch of new ones. So I'm not really, Kyle might know more about it, but you see here that, you see here that all of them are closer to the truth than what you get with just controlling for X. You could, yeah, probably what you would do if I had to guess what I would probably do. You'd have to change it and make the baseline 74 to 75, like this. I bet that'll do it. No, the trimming. Did I say trimming? Oh no, yeah. So look, this is it does not look very good. This does not look very good. These are, maybe I didn't do it right. I just guessed at this. I'm not really positive if I did it right, but 70, 75, 74. Something like that probably would have to do, but I'm not really sure. Oh, so yeah, common support. So there was no trimming that was done. There was no trimming that was done. In my code. No, there was no trimming that was done in my code. So you could though do that. You should definitely probably look at that common support kind of closely. But I did not do it. You would do it you'd have to basically estimate your own propensity score and then, trim it and then redo it probably. Not even positive if that would do it. I'm not really positive how you would do it because then it would re-estimate a new propensity score. But no, I did not lead you to do that. So these are concluding remarks before I give it to Kyle. Including the covariates in a diff and diff design is done for reasons that are different than in regressions more generally. It's not about omitted variable bias. It's about addressing a parallel trends violation. Two-way fixed effects can incorporate time varying covariates, and that places restrictions on the models, whereas other methods don't. Doubly robust and inverse probability weighting will incorporate the covariates into the estimation process through propensity scores and imputations, or both, using out baseline covariates only. And that is it. All right. So I'm going to hand it over to Kyle right now. Kyle, I'm going to make it so that you can share your screen. And Kyle's going to walk us through this other paper. And I'm going to mute my thing.
Great. Let me just pull Discord to the side. I saw a Discord question that I was trying to answer before I took over, but I didn't get quite to it. This about the do file, Scott, for the Monte Carlos. Is that in the causal inference one? I was going to look there.
For the Monte Carlos for what?
The ones you were just running.
Yeah, they're in the matching subdirectory. In labs.
Yeah.
But they're not diff and diffs, Kyle.
Yeah.
It's called comparing to, or it's called comparing dot do, I think.
Okay, great. So I have the Discord chat open now, so I can, as folks ask questions. Okay, so I'll pull open right here the inch. Where is it? Okay, so if I've been sort of making changes as Scott was going. So if you forked the GitHub repository, you can just pull down the changes and you'll have it. But so we're gonna go over this paper. It's and I'm gonna do some live coding of it. So mistakes and all. So we'll see how it goes. So the idea of this paper, this is by Klein and Moretti in 2014. The goal was to basically look at this sort of this very large scale federal policy during the New Deal in the 1940s. The Tennessee Valley Authority was established. You can see it kind of in this map. This is Tennessee, the main area. And in this authority, basically what they did was they dammed a whole lot of these rivers, and they basically brought electricity to the region. Historically, at this point, right around 1945, the Tennessee Valley had very little electricity, and it had very little industry. It was a primarily agricultural economy. It lagged behind the rest of the country. And then they wanted to basically look at what was the change in outcomes from 1940 to 1960 in terms of manufacturing employment and agriculture employment. Okay, the paper is really cool. It does a whole bunch of other stuff, but that's the main idea. Brought a bunch of dams to the area. And so what I'm going to do, I'm going to kind of go through these questions as we go. I think hopefully folks can see this. Maybe I'll make it slightly bigger. I'll load the data set. 1 second. Okay, there we go. Okay, so I'll load the data. What the data is, it's a county by year panel. It's for each county. We observe them 1920 through 1960. There's a variable for TBA that's equal to 1 if you're within this Tennessee Valley Authority region. Otherwise, you have the value of 0. There's a dummy for of treat. Here I can show you. Let's see, DF filter treat equals 1. I'm sorry. We'll say TBA. So this county right here falls within the TBA. You can see the value of TBA is like the treatment dummy, and there's a post dummy, and then treat is equal to TBA times post. So it's only equal to 1 in the post period, 1950, 1960. And these are our 2 main outcomes of interest. And then we have some additional covariates that we're going to use later on in the analysis. So the first thing, question 1, is just estimate a standard 2x2 difference in difference. I'm going to use this package FixEst. If you don't use it in R, it's absolutely wonderful. You should use it. You can basically do anything regression related very quickly. So we're going to use the data set and our regression. We're going to do lawn agriculture and lawn manufacturing. Those are our 2 outcome variables, and we're going to regress that on a dummy for being in the TBA, a dummy for being in the post period, and then a dummy for being in the treat X post, which is our treat variable. And I'm going to set the V code. I'm going to cluster by county code. Okay, so I can run that. I didn't do my instruction set. I'm going to filter to make it a 2x2. I'm just going to use the years 1940 and 1960. And then I'll just I'll call this DID, and then I can make a little table right here. Okay. This E-table functions within the FixEst package as well. I love this package. You can basically do everything you want to. This is just like STab in Stata. So we can see we get this TVA. I'm actually just going to make this even simpler and just do TVA times post. That way it looks more like the standard diff and diff equation. So we have the TVA. That's a dummy variable for being treated, a dummy variable for being in the post, and this TVA X post is our difference in difference estimates. Okay, I won't belabor it too much. We've sort of talked about this a whole lot, but this suggests that the TVA lowered agricultural employment by about 22.8%, and it raised manufacturing employment by 27.7%. What we can then do is we can run the same thing, but I'm just going to show you a little bit of an equivalence. It turns out in the 2x2 case, you can actually use county and year fixed effects, and you'll get numerically the same answer. So, so we'll see right here, we get 22.8%, 22.8%, 27.7, and 27.7. And so it does not matter if you use in the 2x2, if you use it, and actually in staggered treatment timing, which we'll learn about next week, it does not matter if you use county and year fixed effects or a dummy for being in the TVA and a dummy for being in the post periods. You're actually going to get the same the same answer. Okay. Now, does it change the standard error? I believe no. No, it does not. The standard error is actually the exact same when you cluster. If you don't cluster, let's see. It's a good question. The reason it doesn't change is kind of technical, so I won't get too much into it. But yeah, if you do not cluster, they're not the same. But when you cluster, you it's sort of technical why, but yeah, when you cluster, it sort of they are equal to each other. Okay, so it sort of doesn't, it's not really plausible to think that the Tennessee Valley Authority is on the same trend, same counterfactual trend as the of counties outside of the Tennessee Valley Authority. As I already said, this region is quite economically underdeveloped, has a small industrial base. And so in this time, they're actually catching up to the rest of the country. And so, you know, we don't really want to take these things too literally, and we actually really don't believe that that in the absence of treatment, that the growth in manufacturing for the Tennessee Valley Authority would be the same as the country as a whole. In fact, it's quite likely that, sort of given historical our historical understanding, we think the TVA is going to be growing faster than the rest of the country. So let's use a 1920 to 1930. So we'll say 1920 is our pre-period and 1930 is our post-period. And we're going to run a new diff and diff analysis. So to do that, I'm going to have to create a variable. I'm going to call it isPost. Oh, sorry, not is. I'll call this is1930. And that's just going to be a dummy variable for being in the year 1930. So we're going to treat 1930 as the post period, 1920 as the pre period, and then I'm going to run the same thing. So I'll go DAD 1920 to 1930, and what I'm going to do is I'm going to use 1920, 1930. I have my dummy for being in the TVA. But now instead of the post, we're going to use is 1930, and then we're going to do TVA times is 1930. And I make a little table. We see that from 1920 to 1930, the Tennessee Valley Authority, counties in the Tennessee Valley Authority grew 12.5% faster than counties outside of that. That's that catch up I was telling you about. And it appears that law and agriculture employment was declining relative to the control counties. So in effect, this is primarily being driven by the fact that the Tennessee Valley Authority was playing catch up in terms of industry. Okay, now this is just 1 point estimate. Instead, what we can do is we can run a full event study. So to do that, let's see, I'll call this ES for event study. We take our same, these, we're going to say I'll add my county code and my year fixed effects. Let's see what I did here. Okay, yes, I did do that. Okay, so what I'm going to do is I'm going to make a variable. I'm going to call this relative year. In effect, I just for these event studies, you need to interact being treated with the year, and then you kind of want the untreated years to drop out. So I'll make this variable. I'll show you what it looks like for the let's see how this. If you are not in the TVA, relative year is always going to be in 1940. The reason for that is that's going to be our omitted category. But if you're in the TVA, relative years, you go to 1920, 1930, 1940, and so on. And so what I'm going to do is I'm going to use as a reference category 1940, and that's going to drop out the non-TVA counties. And so what I get, I don't want to filter the data. And what I'm going to get is I'm going to get a set of point estimates for 1920, 1930, 1950, 1960. And then I can use this function coefplot. And I can plot the event study for agriculture. You can see it sort of looks like there's a sort of, these point estimates suggest that 1930 is a pre-period, 1920 is a pre-period, and we see that sort of employment was in decline in agriculture, sort of, although you can't necessarily reject the null of pre-trends being 0. the standard errors are too large, but sort of the point estimate suggests there's some pre-existing trends. But when I show you for lawn manufacturing, that's really bad. You can sort of see this growth, dunk, 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 dunk. Let me use iPlot. iPlot does it correctly. 1940, and you can see there's like a sort of a trend that you can imagine continuing outwards. And so we sort of see this pre-existing trends, and you can imagine drawing a line and extending those pre-trends, and it might explain quite a bit of the treatment effect. Although perhaps if I drew a line between these 2 points, we might still have some treatment effect there. Is the event study the reason for the is 1930 a correct choice because of the Great Depression? That's a good question. So 1930 is before. Your question is okay. The question is 1930 a correct choice? I think you're asking instead of 1940, would 1930 be a better reference period? Perhaps, but we still are seeing these sort of pre-trends. That's a fair point. I won't sort of think about it too much. Sort of because the pre-trends are so bad, and so but I mean that's a fair question. What should the sort of pre-period, the reference period be? Maybe 1930 might make sense, but it doesn't really change the story that we see these sort of pre-existing trends that sort of extend outwards. And so you could look for something like a triple difference, but I would think all of the counties in the Tennessee Valley Authority are going to be impacted by treatment. So there's no like there's no unimpacted group or something like this. And so instead, we're going to sort of look at covariates. We're going to use covariates. Like I said, we sort of expect there to be this catch up in this region because they had a low industrial share or industrial base in, let's say, 1920. And so in the sort for historical reasons, we sort of think that those are the counties that are going to have large industrial growth. And so we're going to use these four covariates: agricultural share in 1920, agricultural share in 1930, manufacturing share in 1920, and manufacturing share in 1930. Let me grab this. So the first question says, well, what happens if I just try to control for these linearly in our initial estimates? Sorry. So I'll go back to our initial diff and diff. I'll grab this right here. I'll do DID covariates. I'm going to add these as additional covariates for our 1940 to 1960 estimates. And what do we get? Comparing it to the original point estimates. And we're going to see negative 22.8, negative 22.8, 27.74, and 27.74. So including covariates linearly in the two-way fixed effect model does absolutely nothing. And we can actually, if we look a little more closely, it tells us right here, notes from the estimations. The variables, agricultural share, manufacturing share, have been removed because of collinearity. Okay, so including time invariant covariates does nothing because they're collinear with these county codes. I think for a long time, applied folks sort of understood this would happen and said, okay, well, there's no use of time invariant covariates. What are we supposed to do with them? They're collinear with the county fixed effects. But that's not at all what the goal of covariates, time invariant covariates are in diff and diff. What are we trying to do? We are trying to allow for non-parallel trends based on the value of the covariates. That is to say, allow counties with a small manufacturing share in 1930 to be on a different trend than counties with a large manufacturing share. So in some sense, you want to end up interacting these share variables with a time varying coefficient. Allow the impact of time to change depending on these baseline covariates. Okay, so that's what we're going to do here. This is this is question 5. Okay, what we're going to do is we're going to do outcome regression. We're going to do inverse probability of treatment weighting, and we're going to do double robust estimators from scratch. I'll show you throughout how to do this using a canned package, the DRDID package. But for reasons that will come up later, I'm going to drop counties with missing covariates. So I'm just going to filter out any county that has any missing covariates. I'll show you why at the end, but this drops maybe 300 rows or something like this. What I'm going to do is I'm going to first difference the data. So what does that mean? I'm going to take the data. I'm going to go like this. I'm going to create a D lawn manufacturing. This D stands for first difference. I'm going to sort the data by county, code, and year. And then I'm going to do lawn manufacturing minus lag lawn manufacturing. The first lag, I'm going to do this by county code. Okay. So what does this do? I'll show you real quick what this does so far. I'm going to do a 2 by 2. Sorry. I need to filter year equals 1940 or year equals 1960. Sorry. All of these, I'm going to show you how to do this in a 2 by 2 difference in differences estimator. And then I'll show you at the end how to think about doing event studies with these things. So I'm going to go back to this original 1940 to 1960. So I'm going to arrange by county code year, filter for 1940, 1960, take first differences, and then I was going to show you what this looked like. What do we get? In 1960, we get the difference between this manufacturing. This is Y in period 1. This is Y in period 0. And we get 0.6, which is the same thing as 0.599, roughly speaking. Okay. So I'm taking first differences, and then I'm just going to keep the year as 1960. Okay. So I just have one observation per county. I have the change in manufacturing. I might as well do this. I'm only going to do in these examples manufacturing because it'll take a while and it'll take up a lot of space. But I'll just for good measure have lawn of agriculture here. I'm going to save this in a new data frame called first diff. And now we're going to do sort of all of the different estimators. Okay, it's my first difference data. What I'm first going to do is part 1. It wants me to do a difference in difference. So I can do that with first difference data. I can go like this. I regress the first difference of lawn manufacturing. And I can regress that on a dummy for being in the TVA. And we're actually going to end up with, if you recall, I'm going to end up with well, I know what. Manufacturing, ITBA plus ITBA, I post plus ITBA times post. If I need to filter, county has no missing. Okay, so if I run this one, did I do something wrong? Sorry, what I'm doing is I'm running the standard two-way fixed effects panel version. I get an estimate of 27.66%, and I can run the same thing. I can run first differences just on the TVA dummy, and that will give you my treatment effect. You'll see that they match. The standard errors are slightly different, but I think that's a numerical thing and not, they should be the exact same. Think so. Yeah, I think they should be the exact same. So we can see if you just take the change in Y and regress that on the treatment dummy, that's equivalent to doing this difference in differences estimator. In fact, that should make sense Because what is this doing? Regressing any variable on a dummy takes the difference in means of that variable. So the I equals, this intercept is the average of D lawn manufacturing for the TVA equals 0 group, and this is the difference in means from the TVA equals 1 group to the TVA equals 0 group. And so we can we can actually really think clearly that this is in effect a cross-sectional regression. We're taking D lawn manufacturing is our outcome variable, right? I'll kind of do some pseudocode. This is like yi1 minus yi0 is our outcome variable. And we're regressing that on a dummy variable for treatment. And so we just need the change in outcomes to be uncorrelated with treatment for this treatment dummy to give us our average treatment effect on the treaty. In other words, we're back to the unconfoundedness assumption. We need yi1 minus yi0 to be randomly assigned, to be uncorrelated. That's the latex symbol. You need the treatment dummy to be uncorrelated with the change in outcome over time for us to estimate the ATT. That is our parallel trends assumption. Right? This is equivalent to saying yi1 minus yi0 given D equals 1 has to be equal to the change in outcomes for the control group. These are equivalent, or at least this is technically a weaker assumption because it's only about the mean. This is about full independence, but it's not super important to notice those differences. But as soon as you can like sort of make that connection in your head that we're using the change in Y as our outcome variable, and then we just regress that on a treatment dummy. If we want to now use covariates, well, what do we need? Well, we can say conditional unconfoundedness, also known as selection on observables. We just say, okay, y1 minus y0, that's the change in Y, needs to be independent from the treatment, conditional on some vector of time invariant covariates. Like this. Just drop. I was being lazy, dropping some scripts. And if we believe this, so in our example, conditional on these 4 covariates, you take two counties, one treated, one not treated, to have the same 1920 and 1930 agriculture and manufacturing share. If we think their change in outcome is uncorrelated with treatment, on average the same, then we can use any standard selection on observable type estimator and estimate treatment effects. Okay, so that's sort of the key connection is just take first difference of your data. In the 2x2 case, we just use standard regression treatment effect estimators that have sort of, you cover a whole bunch of in your econometrics 1 class, in causal inference 1 class, if you took Scott's class in the beginning of February, I guess. Okay, so I'll show you the first example. This is outcome regression. How is outcome regression different? Well, the first thing you could be tempted to do, I'll say this is something that perhaps you should not do, but is sort of the easiest thing to do, is just add those covariates. Fixtest lets you do this really cool thing where this is kind of like locals in Stata, where you can sort of say, when I type ... x, put these in for me. So I don't have to, I don't have to type it like that. Fixtest is an amazing package. It's my favorite package in R. It was made by one person, and it's an incredible feat of skill and knowledge. But anyways, so you might just say, okay, well, if we have a selection on observables type strategy, well, the easiest thing to do is to control for X linearly, is to say, take the difference in lawn manufacturing over time, so 1960 minus 1940, regress that on a treatment dummy for being within the TVA, and then it control linearly for these covariates. What is this doing? Well, it's saying, well, we're going to let the change in Y over time depend linearly on those manufacturing shares. So if I, and then we estimate those. There's a problem with this, okay? one of Scott's favorite papers, the Slokzinski and all et al. Papers, not at all. He wrote it by himself. This new, is that in Restat, Scott?
Yes.
Yeah. This goes back to like Enger's 1998 or a whole bunch of these things. When you control for these things, in effect, what you're doing is you're imposing, unless X is quote unquote fully saturated, which is like a set of dummy variables for age or a set of dummy variables for gender or something. If X is continuous, you're going to sort of average over this heterogeneity. And in particular, if you want this, the coefficient on the TVA to represent the average treatment effect on the treated, what you're imposing is that treatment effects do not vary by the value of X. So in other words, the treatment effect for having a small manufacturing share has to be the same as the average treatment effect if you have a large manufacturing share, which we don't really believe in this setting because of this catch-up feature. The TVA bringing electricity is going to help counties that had small manufacturing shares in 1920 more than it helps counties that had large manufacturing shares. So we expect the treatment effects to vary based on X, and so this is going to create some bias in this estimate. And so what we're going to use instead is we're going to use an outcome regression. How does this work? We're going to do something very similar to this. We are going to regress Y. We are going to regress Y on our covariates, but we are just going to use the not treated group, those counties outside of the TVA. Okay, so that's going to produce a set of coefficients. And then what I'm going to do is I'm going to predict for the full data set. That's this new data argument. This is equivalent to in Stata, if you're more familiar with Stata. I'll call this dy0 hat xb. This is equivalent if you know Stata. But I'm going to call this dy0 hat. I'll tell you why I call it that. Okay, it's just a vector of predicted values. Why am I calling it dy0 hat? Well, this is my outcome variable. It's delta y, and I'm predicting it using an intercept plus a set of covariates. But I'm only using the untreated group. So this is yi1 of 0 minus yi0 of 0 is my outcome variable. Because we're only looking at the untreated group, these are the untreated potential outcomes. And I'm learning a model that predicts the change in untreated outcomes. You might call this delta yi 0. I'm learning a model to predict the counterfactual change in outcomes, the change in untreated potential outcomes. And then I'm predicting that out of sample. Okay. For the treated units, I have yi1 minus yi0. That is equal to the treated potential outcome in the post period minus the untreated potential outcome, which of course we can write as yi1 0 plus yi1 0 minus yi1 y0 0. And you can see right here, I'm going to go like this. This is my treatment effect. I'll call that tau. Plus this is delta yi0. And so we fit a model to predict yi0 given these covariates. And we're going to predict that for our treated observations. And so what I'm going to do is I'm going to take the observed, I'll call this delta yi. I should not call it that. That's not what that is. This is the delta y. So I'm going to use dy. So we have the observed change in Y, and we have the estimated change in Y in the counterfactual where you're not treated. And so outcome regression, we can view this as being the mean of dy minus dy0 half. And I'm going to get this variable, the treatment dummy, which is first diff TBA. And I can just average over the treated units, the difference between the observed change in Y and our predicted change in Y for the treated units. And I'll get a treatment effect estimate of 0.2374. Okay. But I'm going to show you, I sort of have in the README these long notes down here. All of these estimators, so the doubly robust DID, the inverse probability of treatment weighting estimator, the outcome regression, and the DID, all can be written in this form. A set of weights W1, a set of weights W0, take the difference in those weights, and then we have a change in Y with this tilde. So for the difference in differences, we have the weights being the treatment dummy divided by the probability of treatment, and then W0 is 1 minus the treatment times the probability of being untreated. And in effect, what that does, if you replace this, and then delta tilde Y is just delta Y, you can do some math, and what you end up with is you get the change in Y for the treated units minus the change in Y for the control units. So it turns out that the diff and diff takes this form, W1 and W0 for these weights, and then just the observed change in Ys. The outcome regression, what do we do? Well, I just showed you how we estimate this model for the change in Y given a value of X. That's this right here. We've estimated this. What we do is we take delta Y and we subtract off our estimate. So that's this right here. I'll call this Y diff. I'll call it dy diff, I guess, which is dy minus dy0 half. We take dy diff is okay, good. We take this difference in Y, so we have where am I? Here I am. The observed change in Y minus our predicted change in Y. This is the delta Y I0. And then we're going to use this weights. W1 is actually going to be this D over the probability of being treated. And then W0 is going to be 0. And so what we get is I can actually show you that this is equivalent to doing this. I will create W1 equals D divided by the mean of D. The mean of D is the probability that you're treated. And so I can show you that the mean of W1 minus 0, which is just W1 times dy diff, is going to give us that same answer. So what I do is I take my observed change in Y minus my predicted counterfactual change in Y. I averaged it for the treated group, and I got my estimate for the average treatment effect on the treated. That's outcome regression. We fit a model to try to predict the change in the counterfactual Y. We predict out of sample for the treated observations, and then we take the difference between the observed and the predicted change in Y, and that is our difference in difference estimate. Okay. For the inverse probability of treatment weights, we're going to use a logit regression. I always forget how to do logits. I don't do them that often. And what do we do? Well, we're going to predict the probability that you're treated given the covariates using the full sample. This family equals binomial is how we do logits in this function. So we've estimated a logistic regression where we're trying to predict the probability that you're in the TVA given these covariates. And then I can use predict on that. Maybe I'll call that logit. I'm going to have the propensity scores where I just predict Now I've gotten fitted values. I can make a histogram of those. I have a histogram of fitted values between 0 and 0.5. I can actually I can sort of assess the overlap condition. What's the best way to do this? I'll do this, jam density. Group. And then I'll make. Okay, so I think I need to go like that. Ignore my ggplot code, not important. Okay, so we have the untreated group. This is the distribution of estimated propensity scores for the untreated group. This is our estimated distribution of propensity scores for the treated group. Sort of intuitively, because treatment is not random, they targeted the TVA. The TVA has a larger set of predicted propensity scores, the distributions at higher propensity scores. Okay. There's some concern about overlap. We see some of these, like some of this high propensity scores. There's really not many, although it's not so bad. There, it's a bit concerning when you get around here, but there's a good amount. So, take this with a grain of salt. Maybe there's some concerns about overlap, but some people suggested trimming. There's some alternatives and sort of practically speaking. But for now, I'm gonna make a different code block for that. Okay. I'll take the propensity scores right here. Okay. So now for propensity scores, I'm gonna use a certain set of weights. These weights are kind of complicated, but they're not so bad. Our W1 is the weights for the treated, which is D divided by the mean of D. It's pretty easy. And then we have W0. This is the weights for the control group. This is going to be 1 over mean of D times 1 minus D times P, the estimated propensity score, divided by 1 minus the propensity score. That's this right here. Okay. And so what am I going to do? Well, I can write this like this. I can write W1 times dy. This is the estimated change in the outcome for the treated group. And then I can do mean of W0 times dy. And that's my estimated change in y for the control group, right? This only takes the value. This only takes a positive value. That you're going to see there's a lot of zeros. And in fact, I can show you this. W0 D equals 1. It takes the value 0 for all of the treated observations. And it takes a positive value for all of the control groups. W1 likewise takes a value of 0 for all the control group, and W1 takes a value of 1 for takes a positive value for the treated group. So this is a weighted average of the change in Y for the treated group, and this is a weighted average of the change in Y for the control group. And so this is kind of like this is a different version of E of yi1 minus yi0 for the treated group minus E of yi1 minus yi0 for the control group. The only difference being that I'm going to put more weight. I'm going to put more weight on observations that have a high propensity score. These observations look the closest to the treated units, so I want to put a lot of weight on these counties. I put very little weight on these. Okay, so in fact, I can show you that. That's a bad idea. I'm not going to try to do that live. But you put more weight on observations with large propensity scores than observations with small propensity scores. And this is my inverse probability of treatment weighting estimator of the difference in difference. Okay, like 0.237. Okay, I'm going to point this node out. This these weights right here. Once you view this difference in differences as just being an unconfoundedness type regression with change in y as your outcome variable, these weights, these are called Horvitz-Thompson weights. For finite samples where you estimate the propensity scores, sometimes you want to use what are called Hajek weights. And you actually do basically the same thing. But instead of using the weights W1 and W0, you're going to divide the weights by the mean of the weights. This is normalizing them. So this thing right here has mean 0, or sorry, mean 1. You just divide it by the mean. And this is going to have better finite sample performance. Okay, so you're going to get a number really close. In this case, you're going to get a number really close to you're going to get a number really close. That's because the mean of this W0 is actually almost 1. If you have really bad overlap, then these things can differ quite drastically. But this basically has better finite sample performance. On average, in expectation, these two things are the exact same, but it's worth saying that the sort of Hajek weights will have a better finite sample distribution. You can see that in Monte Carlo simulations. So the standard error is going to be smaller. Okay, so the last one is this doubly robust estimator. Well, we've kind of done everything we needed to. Now we just need to put it together. We have, well, I'll kind of write it out. We're going to use the weights from the inverse probability of treatment, W1, W0. We're going to use the Hajek weights. And instead of using dy, like we did here, what we're going to do is we're going to subtract off dy0 hat. And this is going to give us our doubly robust DID. Okay. This, you can actually write this in this way. So this is going, what I'm going to do, minus. We can actually take this. This is our inverse probability of treatment weighting estimation. And then we can actually do this. So you can think of this as being the inverse probability of weighting estimator. And then we're subtracting off a bias correction term. It's kind of weird to call it that, but I'm going to call it that. We sort of, you can alternatively, well, I'll leave it at that, and I can show you this matches. This matches if I do DRDID. Oh, it wants me to do it here. I'm going to show you that this doubly robust DID estimator, 2336144, is what DRDID is going to do. Okay. It's going to use the panel data. Once the outcome variable is lawn manufacturing. T name is year, ID name equals county code. D name equals TVA, my X formula is equal to this. My data is my original data filtered to year equals 1940 or year equals 1960. When I run this, we're going to get an error. It's a bit annoying, but ID name has to be a numeric. And so you can do that by using this trick, which is as factor, as numeric, and then it will you'll spit out unique numbers. This is like equivalent to, I think, eGen group in Stata. So it's just annoying. The Stata version makes you do the same thing. I wish it wasn't like that. But anyways, get a FIPS code, for instance, this would work better. I do have a FIPS code. Doesn't matter. So I run this, and I'm going to use est method equals traditional. And it'll spit out the locally efficient double robust DID estimate is 0.2336. And I can actually show you it is numerically equivalent, 0.2336144. And if I rerun my manual version, 2336144. So that is what's happening under the hood. Why use this? Well, A, you don't have to deal with taking first differences in the data and running some propensity score estimation and an outcome regression and make sure you get your weights right. They'll do it all for you, but also you're going to get asymptotically valid standard errors. You can bootstrap and so on and so forth. But I just wanted to show you all of this because as to sort of go under the hood and make sure we all understand what's happening. And because Pedro is a very talented econometrician, there's an improved method which has theoretically smaller standard errors. In this case, they're the exact same. The point estimate changed by 0.0002, but I think if you had a larger data set, I think these answers might look slightly different. In effect, if you remember in like econometrics 1, if you took an econometrics class, you would do if you learned GMM and then you did like a 2-step GMM where you weight by the inverse of the variance covariance matrix, blah blah blah. That's what this does, and it doesn't change your answer, even though it's more efficient. It like basically usually always looks the same, especially with anything that looks like regression. I think I missed a question. Okay, so the last thing I'm going to show you is next week, you're going to learn about staggered treatment timing. Okay, and you're going to use this DID GT function. This is how we're gonna. So I just showed you how we went under the hood of double robust DID. Double robust DID is what's going to be called from this DID function. Okay. So what I'm going to do is I'm going to define this function requires you to have a variable called G. G is the year that you start treatment. In this case, we're going to say 1945. We don't have staggered treatment timing, so there's in effect only one group. But then what I'm going to do is I am going to call DID ATT GT, Y name lawn manufacturing, T name year, ID name county code numeric. D name now becomes G name. This is for if you have units that start treatment at different times, you pass the year that it started treatment. But in this case, there's only the TVA. And so we put that as the year, as the value 1945 for the TVA counties and 0 for the never treated counties. Okay. I give it my X formula, which we have right here. And then I can pass to it the full data frame that has years 1920 through 1960. And if I run this, what are we going to get? Well, we get 0.2336 for this 1940 to 1960 comparison, but we also get a whole bunch of other point estimates. Okay. And then I can use this function ggdid, and I can actually make an event study plot. Okay. For units that are treated in 1945, that's the units that are in the Tennessee Valley Authority, I get a set of point estimates. In 1960, we get that treatment effect estimate we had. And we're kind of seeing, this is quite a bit of noise, so I would not read too much into it, but you're sort of bouncing around 0. And so in some sense, pre-trends have been fixed, but I wouldn't look at this graph and think that you did a really great job. The standard errors are very large. And you really want these point estimates to be really close to 0. In fact, 1950 is kind of what you want it to look like, even though that's a post-treatment period. The reason I think 1950 is quite small is TVA took a long time, like 5 to 10 years to finish. And so 1950 is kind of like a pre-treatment period, although it's after when it started. And so that's why it's kind of near 0. But what you'd really want is like this, and this. Okay. The status code CSDID in the solution is only used for easy plot. Yes, correct. Sanchita asked, Pedro mentioned about inverse probability tilting. Okay, so that's a sort of technical paper. Inverse probability tilting. These weights right here, which I can show you in the sort of printed out form. Take the treatment times the probability of treatment, and then 1 over the probability of treatment, 1 minus D times the propensity score divided by 1 minus the propensity score. These are the standard Horvitz-Thompson weights. The inverse probability tilting weight, imagine you take these and you kind of, you're not really trimming. You're not dropping observations, but you're sort of down weighting even more the observations that have propensity scores out here, I believe. I read this paper like 2 years ago. It's a really smart paper, and it theoretically makes your standard errors smaller, but with sort of all of these things, I don't really see much of a difference practically speaking, but I believe this improved estimation method does inverse probability tilting instead of weighting. And it does this sort of weighted least squares instead of an unweighted least squares, both of which improve efficiency theoretically, and depending on your application, whether or not it makes a big difference or not in terms of decreasing your standard errors. Interestingly, the default in double robust DID is to do the improved method, but in DID, it does the non-improved method, the traditional method. I don't know why it doesn't. They're not consistent, but you want the noisily. So in R, you just call print on the thing. Sometimes functions have custom print methods like this. This has a custom print method. It prints out a table for you. And so I think what Solomon's asking is like, how do I get the coefficients out from this? So I'll just save this. I'll call this drdid. Here's a trick for you if you're an R user. This function str lets you dig into objects. This is like if you're like trying to find, like if you want to know how do I get this number and store it as a variable, start with str, and it's almost always going to tell you. If I run this, you're going to see this object has a custom print method. That's what's making that really nice printing. But you can see it's actually just a list. And so I can go, and it contains these items, and I can just go like this. Because it's a list, I know I can grab from it using the $sign, and I can grab the ATT, for instance. And I can grab the standard. I can grab the standard error. And I can grab the confidence intervals and lower confidence interval, upper confidence interval, like that and so on. If that answers you. Okay, great. Any other questions, or should we call it there? All of the solutions all typed up and stuff are up on the GitHub already. So if you wanted to look at that. But if there's no other questions, I think that's our day, Scott. Is that right?
Yep, it's our day. Kyle, that was fantastic. Thanks so much. Okay, well, we are done for the day. We're going to start staggered differential timing on Saturday And then we'll do differential timing probably over a day and a half, and then we'll do continuous, and we'll sort of wrap it up. Thanks so much, Kyle, for working up this paper. And that's very, very cool to see so much thorough analysis. And I'm going to go back and watch this recording and learn a lot from it. So I'll see you guys on Saturday, and I'll not going to go to bed for a while. So I'm going to hopefully be able to upload this thing on time. Y'all have a great day, and thanks so much for your engagement today. Bye-bye.